So, good afternoon, everybody, and apologies for starting a little late. This is completely and entirely my fault, as I was making a mess with my connection. Just a few brief words of introduction. First of all, I would like to thank everybody for being here, and both the speakers and attendees. And so this session is connected to the session of this morning on quantum security. So you have heard this morning about the possibilities and risks that are present now in the new changing situation where emerging quantum technologies, both in the communication sector and in the computing, are emerging and becoming more and more of a reality. And this afternoon you will hear about an infrastructure that the European community is putting in place for allowing the European community of not only of researchers, but especially of users, industrial users and private users, and also public users as well, to use quantum communication for security and for secure communication. The aim in the end would be to build a quantum internet, but this is the first building block, and this first building block is already a wonderful endeavor, and you will hear about it this afternoon. Okay, so with this, I would like to thank my co-chair, Alessandro Zavatta and Davide Bacco, who you will meet later during the session. And I would now give the floor to the chair of the first session of this afternoon, who is Davide Kalonikov from INRE.
Thank you. Good afternoon. And so let me thank all the organizers, the chairs, for a really interesting workshop that we are going to start. So just a brief technical remark. So we are allowed to use Slack to pose questions, but we have also here a question and answer. I suggest to put the questions, and the speakers can then answer to the question themselves. So we can really use the time to follow the different talks today, because we have several talks and time is probably not enough to collect all the questions that will be generated by these speakers. So I will chair this ground segment session, and we can start with the first talk, that is the tutorial on fiber-based quantum communication, given by Marco Luca Marini, University of York. So Marco, the floor is yours.
Thank you, Davide. So thank you, Chairman. Let me just share presentation. Here we go. And so thank you, and thank you everybody for being here in the afternoon. Thank you, the organizer, for inviting me here to give this tutorial. And it's a pleasure being here. It is unfortunate that the UK is not part of EuroQCI initiative, such a beautiful initiative. But surely there will be more ways to collaborate between European groups. In the end, we are still a part of Europe, at least geographically, I hope. So I joined York last year after 8 years in Toshiba, Cambridge. So clearly my presentation will be heavily biased by this industrial background. And I start here with an example of everything I could touch today in this presentation, because all these activities are based on fibers. and are related to quantum communications. So we could have quantum communications as protocols or quantum devices used for quantum communications. We could go into multiplexing networks and field trials, or even standardization and chip integration. But clearly the time is too short to explain all of these, so I will mainly focus on the quantum communications part, which is the top left diagram shown here. So let's start with a very basic introduction, probably redundant for many of you in the audience, but still useful, worth giving. I've explained quantum communications in the past, and I usually explain it as optical communications without the power knob. So if you are already an optical engineer, you are welcome to join the field. Just forgive about high power, essentially. Typically, classical communications work around 0 dBm, which is about 1 milliwatt, and this is what we consider high power. And if you want to go to the quantum level, you have to turn this knob down to the single photon level. And this is about 7 orders of magnitude lower, minus 70 dBm, around 100 picowatt if you work at 1 gigahertz repetition rate, around 50 nanometers. So this is the range where the magic happens somehow, going between from classical optical communications to quantum communications. So if you accept this constraint, then a few things happen. First of all, at around minus 30 dBm, your standard detectors will stop working, and you have to replace them with the more sensitive detectors, single photon detectors, like shown in this picture. This is based on semiconductors, is a self-differentiating avalanche photodiodes from Toshiba, and this is a superconducting nanowire detector. So this is more compact and inexpensive, and this is more performant, but a little bit more bulky and expensive. Then, if you turn the power knob down, you will have problems in using your standard amplifiers to repeat the quantum signals, and you will need a quantum repeater instead, which at the moment is not yet available, if not partially, as I will briefly mention later on. Then your filtering techniques to isolate the quantum signals from the classical signals will have to be refined. In this example, I show the Raman backscattering associated to sending signals around 1610 nanometers. And this is the quantum signals, which is essentially buried into the noise of this Raman spectrum here. So you will have to essentially work a lot, not only with WDM filters, like we see here. This picture is taken from this paper in Physical Radio X. Coarse WDM filters are not enough. Then you can go to narrow bandwidth filters, still not enough. The quantum signal is here and the Raman tolerance is there. So typically what you want to do, you want to decrease the power control also of the classical signals, not only of the quantum ones. So to get to this point, and then using also temporal filtering and almost getting to the time bandwidth product, you can essentially isolate the quantum signals and retrieve it from other more powerful classical signals traveling in the same fiber as the quantum signals. However, these are somehow a little bit of obstacles you will meet, but then you can gain some more security in this game. Essentially, we can go from computational security to more refined forms of security. I would say this is an epsilon security, which is very close to information theoretic security or to the perfect Shannon security that we all know. So this is the goal of any quantum communications, secure quantum communication protocol. In the past, I received the objection that, okay, but this is useless because optical fibers are already intrinsically secure, even if you use high power, because it's not possible to tap optical signals off continuous optical fibers. I guess we all know that this is false, and indeed it is very easy to tap signals of optical fiber. For example, you can find commercial devices like this one that by simply bending a fiber and taking what comes out after bending it beyond a certain radius, they can steal whatever light is going to the fiber and retrieve the information without the users being aware of it. So this is essentially not the right way to protect optical communications because of a fiber. And you can find on YouTube many videos explaining how to hack an optical fiber in 5 minutes using this inexpensive device. So the proper way to protect information is actually turning the power knob down and going to the single photon level. And on top of that, we should be using also the limiting theorems of quantum mechanics. For example, the no-cloning theorem, which says that non-orthogonal unknown states cannot be perfectly cloned. A quick example here, we have an example in polarization. These two polarizations, horizontal and vertical, are orthogonal. The scalar product is 0, so they can be perfectly cloned. So they're not good for secure quantum communications. Whereas H and D here are non-orthogonal, the scalar product is non-zero, so they cannot in principle be perfectly cloned. And so they could be used in principle for secure quantum communication. Essentially, this is the main idea behind quantum key distribution. We can have an attacker, usually called Eve, on the line, and this attacker is completely unrestrained. They can do whatever attack they want. But if Alice encodes these single photons here with bits 0, 1 using these states, which are non-orthogonal, in some way, Alice and Bob will manage to securely communicate despite the presence of Eve on the channel. And this is quite remarkable if you think about it. So we used QKD to distribute symmetric encryption keys to remote users via a public insecure channel, which is completely under the control of the eavesdropper. There are no assumptions on Eve, and the only assumptions are that Alice's and Bob's devices work as we expect. And this is a very strong requirement. For example, our current cryptography through RSA or other techniques, they usually assume that Eve has a limited computational power. And also the post-quantum cryptography algorithms assume the same. So they can be secure against certain algorithms, but we don't know if they can be secure from other algorithms. Whereas QKD just assume nothing about the attacker, which is very good for future-proof security protocols. Performance-wise, the most important figure for QKD is the secret key rate, SKR, versus loss, or equivalently versus distance, because distance and loss clearly are related in a direct way. So I give here some rough figure about what you can do today with point-to-point QKD. The typical distance you can reach is about 100 kilometers, which is typically 20 dB. And the maximum distance, however, is bigger than that, is between 200 and 400 kilometers, depending on the technology you use, the fiber that you use, and the detectors. And the secret key rate typically is about 1 megabit per second at 50 kilometers. It is quite remarkable that this performance is reached using inexpensive DFB lasers. But of course, the performance depends on the repetition rate and the detector that you use. If the fiber is dark or is a live fiber where other signals are traveling or not, and also on the quantum protocol that you use, for example, if it is based on discrete or continuous variables. However, these more or less are the performance that you can achieve in fiber-based point-to-point quantum key distribution. And you can read more in these couple of papers, 3 papers listed here. Giving you more details about the point-to-point QKD, we can consider just two users, Alice and Bob, a distance L, which is equivalent to a certain loss eta. And then if we simply consider a couple of characteristics of Bob's detector, like the dark counts and the efficiency, the secret key rate will be an arbitrarily complex function of this distance and these other parameters. We can plot the secret key rate on the vertical axis here and the distance or the channel loss on the horizontal axis here. And I have put here some selection of significant results about QKD. Clearly, the soft spot is in this corner where you have a high security rate for high distance. But if you look at QKD experiments so far, and this is just a selection of, let's say, the historically most meaningful ones, you can see that they all arrange in this section of the figure and below this line that I manually drew in this figure. So essentially, it's very difficult to reach the soft spot. And in fact, people ask the question, can we ever reach this soft spot with a QKD protocol? And the answer is in this repeaterless secret key capacity, which is a bound found by people in York, Pirandola, Lavenza, Tagliani, and Banchi, that basically have studied the problem and have come up with a final response about it. You cannot overcome this bound, whatever you do in QKD with any protocol that you might use and any technology. So this is a very interesting and strong response to the question where we can go with QKD. So there is quite a gap between this bound and the current experiments, as you can see. And clearly the question is, can we do better? And can we ever overcome this bound? In the next, I will present a couple of solutions to overcome these bounds in fiber-based architecture. The first one is based on trusted nodes. However, this will have some sort of caveat. And the second one is so-called twin field QKD and is a form of one-node quantum repeater. And just to mention, if we had an ideal quantum repeater, we would be able to follow this line, which is the secret key capacity corresponding to one-node quantum repeater. So this is the repeaterless one, 0 nodes, and this is a one-node repeater. And then you can imagine if we have 2, 3, or more nodes, we would have a line that is increasingly flatter and flatter until we reach the ceiling of this figure here, essentially. However, going to trusted nodes first. What are trusted nodes? Well, it's a simple solution to essentially take the point-to-point QKD that we have here and reach arbitrary distances by simply repeating the scheme using something like depicted in this diagram here. We have Bob, who lives in the same place as Alice in the trusted node, and this area is not attackable by the disruptor by something, so they can retransmit the key. Bob can retransmit to Alice 2 to see that he receives from Alice 1, and then Alice 2 can transmit to Bob, again in a secure way, and then Alice 3 can regenerate the key and send over to the final Bob. So with a chain of nodes,
Marco, your audio is a bit less better than before. So
okay, sorry about that. I guess that's my connection at home.
No, now it's okay. Now it's okay. So you can go on. Thank you.
Thanks. So eventually I was saying that you can reach from Alice to Bob through a chain of trusted nodes, if of course you assume that nobody can attack the trusted node. So a couple of notable examples of backbone networks that are built on a chain of trusted nodes are these two, one in China and one in Italy, both about 2,000 kilometers long. And in this case, in China, they go from Beijing to Shanghai with about 32 trusted nodes along the way. And then they, in each main city, they stop and they develop a star network. And I think we will hear more later on today in a future talk. And if you want to know more about the Italian quantum backbone, then you ask our chair, because this is managed by INRIM. And indeed, its main purpose is to disseminate time and frequency across Italy, but also to have quantum applications. And for example, in quantum communication, I believe there has been already tests between Turin and Bardonecchia, and now between Santiago and Bardonecchia, and also in the Firenze area. I also would like to show this other picture, which is not strictly a backbone network, but is very inspiring in my opinion, because it's essentially the European time frequency dissemination network. Some fibers are already installed, others are on the way, but essentially gives an idea of what the EuroQCI could be in the next future. So now we have learned about this trusted node architecture, and can this architecture actually overcome this repeaterless key capacity bound? So does it qualify as a quantum repeater? Well, this answer is yes and no, and let's see why. I take again this plot that I have already shown before, and I now imagine to put a trusted node here at 100 kilometers after 20 dB. And in this case, I can repeat the signals in a classical way, if you remember the schematics of the trusted node, so that essentially my curve starts equal to this one, but now starting from 100 kilometers up to 200 kilometers, where I can imagine to put another trusted node and repeat the curve to reach 300 kilometers, and so on and so forth, so that I can essentially cover the whole distance with a chain of trusted nodes. So apparently this overcomes this repeaterless secret key capacity bound. It's quite clear that is above it. However, strictly speaking, it does not overcome this bound, because the assumptions are clearly different. On this line, we have no assumptions in the intermediate space going from 0 to 500 kilometers, whereas in these lines, we assume that every 100 kilometers, we can regenerate classically the information and retransmit to the next segment. So these are just two different assumptions. They are not the same. And clearly the practical implications are very different, because in one case, you have to protect many trusted nodes. In the other case, you don't have to protect anything in the way, just the initial and the final points. If we had a one node repeater secret key capacity, then this would be the curve that we would see, and we could reach the final point without assuming anything in the way. So how do we go from trusted node to untrusted nodes? Well, we simply change the picture here, and basically that's done, right? What is an untrusted node then, or a quantum repeater? Well, we know in theory how to build a quantum repeater. However, in practice, full-fledged quantum repeaters are still outside of the reach of current technology. There are many groups around the world working on it, but still a little bit outside. At the moment, what we can do is building a partial quantum repeater or a one-node quantum repeater, and in so doing, we can nearly double the distance of QKD. And this is what twin-field QKD is, and that's a quite recent development introduced in 2018. And in that case, Charlie receives signals from Alice and Bob and mixes the signal in a way that it allows it to repeat the information from one user to the other. This is very similar to the so-called measurement device independent QKD that I'm sure many of you already know, but is somehow different in the result and in the performance. Let me also mention that this is useful for star networks, because it's very easy to connect pairs of users through an untrusted node that is called Charlie in this case. So just to give a notion about what twin-field QKD is, you can see a sketch here, which was in the original paper. Essentially, you can implement it without single photon sources and without expensive technology, just using laser sources, intensity modulators, phase modulators, variable optical attenuators, random number generators, and then a little bit of phase locking between the two users, Alice and Bob, which is actually the tricky part, because essentially this qualifies as a very big interferometer where you should have coherence between this point and this point when they interfere infrarly, which could be hundreds of kilometers far apart. And to guarantee the stability of this huge Mach-Zehnder interferometer, clearly you need control over the phase of these lasers here. This is more or less the equation that catches this phase stabilization. You have to stabilize the frequencies between the Alice's and Bob's lasers, and at the same time you have to stabilize the fluctuations in length that you might have on the fiber that is deployed between Alice and Bob. This clearly is not easy, and you can see here examples of wild fluctuations. When you reach 100 kilometers, you experience phase fluctuations in the order of radians or every milliseconds, which is thousands of radians every second, and it's not at all easy to stabilize this interferometer. However, if you manage to do so, then you can gain something from it, as I can show in this picture here. This is the same picture I showed before for the QKD experiments, and then on top of this, I now add the results from the FQKD experiment. This was the first result of this kind, and you can see that the red diamonds now go through this this blue gap that is depicted here, and even overcome the SKC0. And this was a first back in 2019. And then other experiments came repeating these results, and in some cases also improving it, and reaching quite remarkable distances. So somehow these are the recent results about the FQKD, and the fact that it overcomes the SKC0 means that essentially this qualifies as an effective quantum repeater, although with a single node in the middle, which is depicted in the schematics here. Now, I'd like to mention, to conclude, a couple of recent results. So if I just extend the plot a little bit and I obscure the previous results just a teensy bit, one of the recent results is this one. Essentially, recently, the Toshiba people have reached 605 kilometers distance in fiber. So they have overcome for the first time this boundary that we had around 600 kilometers. And you can see, it's interesting to see that basically all these experiments for TFQKD show a T-rate slope that is parallel to the same slope that we have ideally for a single node quantum repeater. And this clearly allows to cross this line and go to very long distance. Another interesting and remarkable result is this one that has been achieved in collaboration and mainly by INRIM, and is a field trial at the distance of 206 kilometers, 75 dB loss in total. So to have a comparison, you have to consider that before that, let me also mention that recently this has been further extended to 430 kilometers in China. And to understand the progress, let me draw this line, which essentially includes all the previous field trials that were tried in QKD. And you can see that there is an improvement of around 40 dB. So this is quite an impressive result, and it has been obtained just in the overall duration of 2 years, more or less. So I do not have time to go in details for these results. I, however, want to show a couple of notions about this experiment here and this experiment there. So one slide for each. This is essentially the setup that was used to overcome the 600 kilometers in a fiber-based experiment in the lab. you can see that only lasers and standard components like phase modulators or intensity modulators were used. In this case, the main idea is to lock one of the two lasers to the lasers that Alice and Bob are locally using through some servo fibers, so that the wavelength, at least of these two lasers, is the same, and they can eventually interfere entirely. And for doing proper interference here, I used a second wavelength, which is L2, so that these two wavelengths are very close, spectrally speaking, so that information on one wavelength can give information also on the other wavelength. One was used at the classical level, so that the detection rate was high enough to compensate the wild phase fluctuation, and the other was used at the quantum level to transmit the quantum information. And you can see in these plots here how the phase fluctuations was controlled. The violet background is essentially a wild phase fluctuating, whereas the orange one is the one that you obtain after compensating in phase. And the phase compensation is done here in Charlie. So it's local and is not prone to the round trip over the long fiber. And this was essentially the main advantage of this scheme. And this other one is the field trial between Bardonecchia and Santia, over 200 kilometers.
Marco,
yes, tell me.
Marco, 2 minutes.
Yep. Oh, thank you. Yes, just in time. And this has been done mainly by the INRIM group, where they managed to obtain and see a quantum interference here in Turin. So Charlie was placed in Turin, and then Alice and Bob were in Bardonecchia and Santia. And we could call this system as a coherent dual band stabilization, because also in this case, two different wavelengths were used, but these two wavelengths came from somehow were phase locked through an optical comb, so they were phase related. And in this case, when you retrieve the phase information on one wavelength, you exactly retrieve the phase information also for the other wavelength, which was not the case in the previous implementation. And among all the results, I selected this one, which shows that essentially you can, using this compensation, you can keep the QBR below 1% up to a time scale that is in the order of 1 second, which is indeed quite impressive, which essentially means that you can freeze the phase fluctuation almost completely and go on with your quantum communication. So this brings me to the conclusions, which I will quickly read. I think fiber-based communications have greatly expanded in the last decade, and even more so in the last 3 years, where we have witnessed the fiber-based one-node quantum repeater for the first time implemented, and they have reached the very long communication distances in the order of 600 kilometers and 100 dB loss. And we also have extended a lot the reach of field trials from 90 kilometers to 200 kilometers first, and then even 500 kilometers, so that we can now link important cities, for example, Rome and Milan, or London and Paris, and this would be quite nice to do in the future. And let me conclude with some advert. Thank you for the attention.
So thank you very much, Marco Luca Marini, and also you have been perfectly on time. Thank you also for this. As I suggested at the beginning of the session, if you have any question, we can really use the question and answers, and the speaker can directly reply. In this way, we can really stick on the agenda that is also quite dense. So this is giving me the opportunity to give the floor to our invited speaker, Chris Irvin, from KITS Quantum Security, that is going to talk about integrated quantum photonics. So, Dr. Irvin, the floor is yours.
Thank you very much. And you can hear me all right?
perfectly.
And I'm just trying to share the, sorry, my screen has of course decided to back up. Let's try this one more time. Joys of doing stuff in the modern world. Can you see a screen?
Yes, indeed.
Cool. Thanks. Hi, my name is Chris Irvin. I'm actually just finishing being a lecturer at the quantum.
Sorry, you switched in a not full screen mode. So you started in a full screen and now
something else.
Yeah, you want this or you? Okay.
Let's try one more time. Sorry, obviously I'm not doing too well with PowerPoint today. If I do it this way, what about this? Better? Back to full screen?
Okay, now it is full screen. So let's see if this stays like that.
Let me know if it goes out of full screen again.
For sure.
Thanks again. My name is Chris Irvin. I've just actually finished as a lecturer in quantum technology at the University of Bristol's Quantum Engineering Technology Labs, mainly because I'm also the CEO and a co-founder of KETS Quantum Security. We're trying to commercialize some of the stuff we did at the university. So this is going to be a little bit of a schizophrenic presentation, part startup, part academic, because we started in with the original work, the Quantum Communications Hub. Marco and others are in it as well. We were at University of Bristol for it. And this is where we developed some of the sort of the world's first chip-to-chip, certainly the QKD experiment and some other things as well, which I'll tell you about. I also had a hand in setting up QTech, this quantum startup incubator, which I think is now just shy on returning 12-to-1 on its money, and KETS came out of that. So KETS is trying to commercialize this chip-based approach to quantum encryption, and I'll try and give you a quick outline of sort of what we do in KETS as well, and the next sort of projects we're looking for, because hopefully maybe even some in the audience can get involved. So really, it's only a 15-minute talk. My goal is to give you a high level sort of broad overview of the work we do and signpost you to some of our papers. Right, so I'll start in the startup. So at KETS, we are trying to combine the power of quantum technology, sort of QKD devices, QRNG, to solve some of the most important sort of security challenges on the planet. And it is good to take a step back for just a second about the problem we're trying to solve, because it's easy to get enamored with the technology, but this is the problem we're trying to solve, is this beautiful sort of 5G world we've been promised. Because connected healthcare, connected transport, all these things are good things that'll bring benefits. But if you talk to people doing and working on sort of implementing it about security, they generally sort of give you one of two answers. Either it's done, and really what all they mean is they're using sort of industry standard techniques, or it's someone else's problem. But if you dig in a little bit, these industry standard techniques are rapidly approaching their end of shelf life. Most of us know, and work in quantum computing, that it's coming on in leaps and bounds, with the likes of Google and Intel sort of getting involved. And it's gonna, it really will break everything we currently use. And I guess for it being someone else's problem, we've decided at KETS that we can have something to play here, and taking it sort of as our mission to help protect what's now, the most valuable resource on the planet, which is information now. I'll back up though. How did we get here? So this is back to work in academia and at KET Labs, where we did, certainly at the time, the world's first chip-based quantum key distribution demonstration. So we have a nice indium phosphide transmitter in the top left there, and it was actually a transceiver. It could be a receiver, but slightly higher losses. So we built a silicon oxynitride receiver on the bottom right. And it's indium phosphide, the transmitter, so you can pattern a laser on it. That's those 3 prongs. You can pattern 10 gigahertz modulators in it, embedded in Mach senders to encode and manipulate your quantum information. And so we did it with time bit encoded qubits. So early and late is our 0 and 1, or spread the pulse across the 2, with a phase is our 2 bases. It was using weak coherent pulses, so we used a laser sort of dialed right down and attenuated, and decoy states to get you the same sort of rates you would expect with a single photon source. And the chip was really nice. It actually could do 4 different protocols. So it can do the standard DB84 protocol. It can do coherent one-way, so COW. It can do differential phase shifts, DPS, and it can actually also do reference frame independent QKD. And you can see the paper reference there and some of the important sort of metrics. So if you take maybe DPS, we were clocking our transmitter at about 2 gigahertz. getting nicely conditioned Q barriers sort of in the percent range, and get about half a megabit per second worth of key over about 20 kilometers of fiber, which certainly at the time was comparable to sort of state of the art. From there, you do the next obvious thing. I mean, this is the beauty of the chip-based approach, is as soon as you have one device that works, you can start literally going to town on sort of Control-C, Control-V, and tiling, patterning these devices on the same chip, basically. So we did exactly that. We took two independent transceivers now, transmitters, and you can actually tune their wavelength. You get about a nanometer of temperature tuning if you just sort of heat up and cool the chip. And then the two Bragg mirrors on the end of the laser, if you apply different voltages, you can tune their wavelength by about 8-9 nanometers. So you get about 10 nanometers in total. So we took two chips and then put it into a wavelength division multiplexer. We sort of tune them so they're separated by a channel. We also offset them by about 90 degrees because you have a little bit of overlap at the tail end just to sort of decrease the noise. And then the chip we actually showed on the previous page was a little bit more complicated than that. It had a DWM, a demultiplexer out front of it, and actually two receivers on it. In terms of the actual sort of experimental results, I mean, none of them are surprising. If you run these things separately, then you get sort of 2% error rates and 300 and 800 kilobits per second of secret key, and you turn them on together and you basically add those rates together. So it's a pretty simple demonstration, but it shows you how you can scale up rates, another sort of avenue towards scaling up rates. And also in today's sort of internet and networking, we're used to being able to send signals to many different people. So if you suddenly have a chip that has 10 connections, they don't all have to go to the same person. They can go out into much more of a rich network fabric that we're used to. And then the next thing was showing how we could do this in silicon photonics, because that's where you'd like to end up if you can, because that's what everything is made of. The processors and CPU that goes into your laptop, into your cell phones. And while there's no light sources, easy light sources in silicon yet, we do have some ideas, as do others. And I think currently we're still maybe one of the fastest in silicon. Certainly at the time we were, and it was based on this fairly simplistic, nifty encoding circuit, but it was absolutely sort of essential because it lets you bias your devices. So there's the block sphere up in the top right-hand corner, basically up at the Y state, so that you can then hit the Z states, the X states that you need to with a pi/2 phase shift. And it was essential because we used carrier depletion modulators, and they couldn't go the full sort of 2 pi range that you'd otherwise need to create your 4 signal states. And even more than that, they had phase dependent loss. So you sort of needed this so that you were doing the same amount of phase in any direction. So the photons that came out looking indistinguishable. And this let us clock these things up at gigahertz, because otherwise we would have suffered from sort of orders of magnitude slower speeds. So we did a couple of different experiments there. We did cow again. You can see we clocked it at about 2 gigahertz with about a percent of Q bar and almost a megabit per second worth of secret key out of it. We also had some devices that brought the paths together in a 2D grading coupler, so we could actually transition and translate into polarization encoded qubits, and you can see some of the stats there. And we did the straight BB84 time bin encoding as well. At the same time, others in CATS now were working on silicon photonics for a quantum random number generator, because silicon photonics has detectors that you can use. It doesn't, again, have the light source yet, but for this experiment, you pipe in a laser to a beam splitter, you get vacuum fluctuations in the other port, and basically those vacuum fluctuations get amplified, and you measure it in a Hobodyne detection measurement. So you're basically measuring the quadratures of the optical vacuum states. You go through a couple more steps to discretize what amounts to voltages into different bins. From that, there's both classical and quantum noise. You estimate the classical noise to remove it, and put the whole thing through basically a big hash function to end up with a nice flat random distribution from your quantum data. And again, it's a chip-based thing that you can get gigabits per second and upwards of random key, or well, randomness, small form factor, room temperature operation. And then one of the last things, technical difficulties, but I caught the tail end of the last presentation, is measurement device independent QKD, which you just heard something about, because there are examples of sort of quantum hacking of commercial and experimental systems, and 90% of them are usually attacking the detectors in the system, either through blinding them with strong light or monkeying the timing of signals. There's a number of different ways, but luckily, someone came up with this MGI QKD idea where you actually hand your detectors to your adversary and get them to do a joint measurement on then Alice and Bob having transmitters and sending BB84 states into this central adversary. And they make this joint measurement, as you sort of just heard. The first step towards that is doing a Hong-Mendel interference to show that we can now interfere two independent chips. And we sort of, you can see in the bottom left, we've artificially separated the spectrum of the lasers to see, to show you just how indistinguishable they really are when you bring them back together. And so it's weak coherent pulses, so you can only do a Hom dip down to about 50%, and we got 46.5%. So very, very close to the bottom of that dip. And then in follow-up work, actually put all the other mechanisms and equipment you need to do full QKD, clocking the systems at sort of 2 gigahertz. Again, in the X bases, you're only going to get about a 25% Q bear because they're weak coherent pulses, but it's, you can still, there's still security proofs that show that it's secure. And then the Z basis is well below %. That's where we got most of the key from. And so over 25 kilometers of fiber, we can still get a secret key rate that's now immune from detector side channels of about 12 kilobits per second. So now sort of switching tacks for a little bit. At KETS, we've sort of moved well beyond these early experiments, because if you came and saw them, they literally were hung together with Scotch tape. And now figuring out how to miniaturize them into using these cutting edge integrated quantum photonic chips into actual products. So quantum demo kits is what we're calling them. Our random number generator 1 was actually ready in January of last year, and you'll see a little bit of some of the things we've done with it in a second. And the QKD one, I mean, this lovely COVID pandemic has slowed us down a bit, but it's almost ready. And so this is continuing sort of on in our roadmap to get these out as quantum demo kits to customers. And this is a key part of our activity right now, is actively getting this out into real world use cases. Some are better than others, but we sort of learned something from each of them. And I wasn't quite sure what I could share when I first put the talk together, but I'll share what I can, some that we're really excited about. The first was an Innovate UK funded project called Kudos, where KETS, Airbus, and a couple of partners worked together to demonstrate sort of a low swap, a low size, weight, and power QKD system operating between a drone flying around in the sky and a ground station. And it was really only possible with this chip-based approach, because I think we had a 2 kilogram weight limit, and you can see our green board, our transmitter, we got it down to about 750 grams. And it's sort of the precursor to scalable networks in the sky when you think about UAVs, planes, high altitude platforms, satellites. And we're continuing this in a feasibility study with Airbus as well, called VISAT QT. Second thing we've done is engaging.
Sorry, yep. 2 minutes.
2 minutes, yep, we're almost done. Thanks. Is in the telecom space, engaging with BT, Toshiba through this ITASEC project, where we're really focused on sort of basic device development and demonstration into fiber networks and with end users. So we're doing a couple of different use cases. Two of the most interesting there, one's with tethered drone systems. So it's putting up sort of a flexible mobile quantum encryption bridge that can then sort of beam quantum keys with a tethered drone flying in the air. So you can think secure sensing and surveillance. And another one is with Dashboard, where we're doing securing sort of oil and gas pipeline monitoring. And the last one is we're on a program with Thales called Cyber at Station F to explore how our technology can be used to touch their businesses, basically. And ended up collaborating actually with a post-quantum startup to do a demonstration. So we piped randomness from our QRNG, their post-quantum algorithms that they incorporated into a very popular sort of open source encryption library. And at the end of the day, did a digital document signing demo in a quantum safe way. And so one of the very last ones, the highlights, is we're now part of a next new exciting POC. The whole session is around EuroQCI, this larger project that's going to put down a quantum safe network across Europe. And France is one of the most sort of active in building a regional one in Paris. So we're going to provide equipment to support the setup of a quantum safe backbone testbed going across Paris to launch sort of future QKD services. And it's a great opportunity to get involved, either as an end user or as a researcher, because I do know the project is looking for postdocs, possibly PhD students as well. So do get in touch if you're interested. And I think that's it. I mean, in terms of what comes next, you've seen some of our proof of concepts, and we're eager to do more. We're starting to get a lot of interest in demos, field trials from customers, which means that we're expanding and hiring. So in fact, we're actually going to open a Paris office, our first international office to support Paris QCI. So if you're interested in doing any work with us, please get in touch. And I don't think there's questions live. I think they're in the Slack channel. So I'll happily turn my attention to Slack to answer any questions that people might have. Thanks very much.
So thank you, Dr. Reuben, for the very interesting talk, and also thanks because also you were perfectly on time. So again, I suggest to pose questions to our speakers using the question and answer box. And following the agenda, we can now move to the next invited talk, that is Metropolitan Fiber-Based Quantum Communication, given by Ilaria Vagniluca from CNR Institute of Optics and University of Naples. So, Dr. Vagniluca, the floor is yours.
Yes, I will share my screen.
So first we can hear you well.
Okay,
Good
and
start.
this is my screen.
The screen is
Can you
still
see
to come. Not yet.
Okay, let me retry. Okay.
Okay, now it's starting. Okay, we can see it and it's full screen.
Okay, perfect, thank you. So hello to everyone and thank you for organizing this online workshop. Yes, about me, I'm a PhD student in quantum technology, and my PhD work is focused on quantum communication and quantum key distribution. So today, during my presentation, I will show you the recent experiments, our recent experiments on metropolitan fiber-based quantum communication, which means to test quantum protocols over typical distances of tens of kilometers, which are the typical lengths of the fiber optic links that are installed underground in metropolitan areas. Okay, so I will start with a brief introduction on our research group, which is based at the National Institute of Optics in Florence. Then I will present our recent test in field of metropolitan quantum communication, which include a field trial in Florence and also some preliminary experiments that we made over a multi-core fiber link, which is installed underground in the town of L'Aquila. Finally, I will tell you about some alternative quantum protocols and setups that we have developed and tested in the laboratory in preliminary experiments by exploiting high-dimensional quantum states. So here are the people that take part in our research group of quantum communication. As you can see, the majority of us belongs to the National Institute of Optics, even if we are in very close cooperation with the Technical University of Denmark, and in particular with the group of Davide Bacco from DTU Photonics. Our main lab is located in the Arcetri headquarters, located in the countryside of Florence, but still very close to the city center. And additional laboratories are located at the European Laboratory for Nonlinear Spectroscopy in Sesto Fiorentino. And also a new lab has been launched very recently at the Science Park area of Basovizza in Trieste. So after this brief introduction, I'm going to present some of the recent works of our quantum communication group, starting from the very first work that is a field trial of QKD based in Florence. So the first thing to say about this experiment is that it was actually the first demonstration of QKD over an installed fiber link to be performed in Italy. The second thing to say is that the fiber link that we tested is actually a portion of this huge fiber network that someone has already mentioned before me, covering the whole country and provided by the National Institute of Meteorological Research. This fiber network has the advantage of being totally dedicated to research activities, and for this reason it can be the proper infrastructure for the future Italian quantum backbone, thus enabling large-scale quantum communications over the whole country. So, referring to our experiment, the fiber link we tested is a dark fiber of about 20 kilometers, connecting the Lens laboratory in Sesto Fiorentino to a telecom data center situated more downtown. As you see here, at the other end of the fiber, there is a mirror, so the light arriving here is reflected back to the laboratory at Lens, where both the quantum transmitter and receiver were located. Here is reported the experimental setup that we employed for quantum communication with time bin encoding. As you can see, in the transmitter setup, we used two different lasers emitting at two different wavelengths in the telecom window. One laser is used for quantum state preparation, while the other is a classical light for providing a synchronization signal between the two stations. So the two lasers are injected in the same fiber and then are separated at the receiver with a dense wavelength division multiplexing filter. So with this configuration, we demonstrated a continuous and stable quantum communication over 4 hours with an average key rate of about 3.4 kilobits per second. Okay, so this was about the field trial in Florence that, as I said, was performed over an installed telecom link of standard single-mode fiber. However, there exist other types of fiber links, as you see here, such as the multi-core fibers, which consist of many cores within the same cladding. And this special fiber type usually exhibits basically the same transmission losses of the standard single core fibers, but also it exhibits a very low crosstalk between the different cores, which enables the transmission of path-encoded quantum states with, as you see, the information encoded in the different core of the fiber and also in their superposition. In particular, as shown here, a multi-core fiber with 4 cores enable the encoding of high-dimensional quantum states, where each photon is carrying 2 bits of information instead of only 1 bit per photon. So, since this kind of fiber was introduced recently, at present there are very few multi-core fiber to be deployed all over the world. And one of these fibers with 4 cores was installed underground in the town of L'Aquila, with an overall length of 25 kilometers. So in this case, when using path encoding quantum communication in multi-core fibers of this length, it is fundamental to keep stable the relative phase between the different cores over the whole acquisition time. And so in order to test the feasibility of quantum communication over this multi-core fiber link installed in L'Aquila, we carried out some preliminary tests of phase stability that you can check in this preprint paper here. In particular, as shown here in the plot, we successfully tested an automatic setup for active phase stabilization, which is able to lock the relative phase between all of the cores by compensating the drift that naturally occurs and that you can expect and 25 kilometers of length. So by using a classical laser propagating through the 4 cores of the whole fiber length, we demonstrated a continuous phase stabilization over 10 minutes, as we reported here in this plot. So to conclude, I would like to show you some recent tests of alternative protocols of quantum communication with high-dimensional encoding that we performed in the laboratory. As I already mentioned, by preparing high-dimensional quantum states, it is possible to deliver 2 bits of information for each single photon, which is the case here of 4-dimensional QKD, instead of only 1 bit per photon, which is instead the case of standard 2-dimensional QKD. So to implement high-dimensional quantum communication, it is necessary to enlarge the dimension of the Hilbert space, which means that now each basis has to include 4 orthogonal quantum states instead of only 1 or 2. So what we did in the laboratory at DTU during my external stay in Denmark was to test and compare the performances of these 2 protocols that you see here.
Sorry?
Both with, yes.
2 minutes.
Okay, thank you. So we tested these 2 protocols with time-bin encoding, which are the 2-dimensional protocol with 3 states, which is the same that we tested in the Florence field trial, and this alternative version of the 4-dimensional time-bin protocol that we proposed in this work. So specifically, this smart choice of 4-dimensional basis makes it possible to simplify the experimental setup for high-dimensional quantum communication, which allowed us to employ essentially the same apparatus to test both protocols without introducing so any expensive component in addition to the 2-dimensional setup. So in this configuration, by using the same amount of expensive resources of the 2-dimensional case, we demonstrated at short distances an enhancement of the key rate by more than a factor of 2, as shown here in the graph. So finally, this is my last slide. I would like to mention the improved version that we proposed of the so-called round-robin differential phase shift protocol of quantum communication. In this protocol, the information is encoded on the relative phase of consecutive laser pulses, which are assembled in packets of fixed length. And at the receiver side, each packet is measured with a Mach-Zehnder interferometer by setting a random delay. So in this process, the 2 pulses of the packet that interfere with each other are picked at random, and the relative phase constitutes the secret bit. And what makes the round-robin protocol interesting is the fact that to extract the final secret key with the privacy amplification procedure, the standard procedure, there is no need, in this case, to monitor the noise over the communication line, because in this protocol, the information leakage to a potential eavesdropper can be bounded only with the already known parameters, such as the path length L. So in our work, we propose a high-dimensional version of this protocol, where 2 bits of information are encoded in each packet by introducing 2 non-orthogonal bases exhibiting the 2 different intensity profiles as depicted here. Here, for each packet, 1 bit is encoded on the relative phase of the interfering pulses, as in the original protocol, while a second bit is encoded in the additional time-being degree of freedom that we introduced. So, to conclude, by comparing the 2 protocols with numerical simulation, we demonstrated that the additional time-being encoding that we introduced makes the whole protocol more tolerant with respect to the errors arising from the interference, as shown here in the plot. So for this reason, we believe that our improved version of the round-robin protocol can be very useful in practical system of quantum communication when the environmental conditions prevent the original protocol from being efficient. So with this, I conclude and thank you for your attention.
So thank you very much, Dr. Vagnidou. And it was really interesting to cover a lot of hot topics in quantum key distribution. And so we can also move forward to cover a hot topic that is a more general quantum communication topic. So the next invited talk is about quantum random number generators. And it will be given by Davide Marangon from Toshiba Europe. So Dr. Marangon, the floor is yours.
Sorry, Davide, sorry to interrupt. I think we do have a problem with Marangon at the moment, so I suggest that we switch and we move on with Tommaso Chipinti, and then we try to recover later, if you agree.
Okay, perfect.
Thank you.
Perfect. And so we switch and we move to the agenda with the invited talk on quantum telecom systems. And this will be given by Tommaso Occhipinti from QTI. And so Dr. Occhipinti, the floor is yours.
Hello, everybody. Give me 1 second that I turn on my presentation.
So again, we can hear you very well. So we're not given. Okay.
So you see my screen, I think.
Yeah, we've seen that.
This is the presentation.
Perfect. Perfect.
Okay. So first of all, thank you very much to everybody, to the organizers, and to giving me the opportunity to present to this important Congress this new company. So we are moving a little bit from pure research activities to a more business topic right now with me. The company is called QTI, and I'm presenting as the CEO of the company here. So who we are? We are an official spin-off company from the CNR, from the National Research Council in Italy. We created the company just in the last month of 2020, and our headquarters is in Florence. We are a team of quantum experts and also entrepreneurs. So we have both the expertise of the research and the expertise of making, let's say, companies starting from as a startup and growing as a full company. So we have these two expertise present in the company. Our technical expertise is on fundamental atomic, quantum optics, and solid state, lasers, and also optical telecommunications, both spatial and terrestrial. What we do? We engineer, we design, let's say, we developed, and we produce reconfigurable quantum key distribution architecture and quantum system. We have a special aim for selling our products to private companies, but also to governments and, of course, research institutions or for research laboratories. In this slide, you see a brief outline of our products. We have basically two products, P1 and P2. They are both characterized by three main points. We are plug and play, so they are easily deployable and reconfigurable in the field. We incorporate inside our physical layer a multi-standard system. So this is why we say that we are reconfigurable. And also we paid a lot of attention on the supply chain. We think that to develop something interesting for the commercial use, we have to pay attention to be at least European, let's say. So our third-party companies producing some parts of our systems are basically based in Italy and in EU. Our first product, P1, is a secure key generator. It is based on a proprietary QKD engine. So the physical layer is embedded in the system. It is a plug-and-play system based on two rack-based appliances, Alice and Bob. And at the end, the secure key is stored locally or used directly from the appliances, from the Alice and Bob units. The P2 is the second product, and it is an end-to-end encryption system. So again, we are using on both sides our QKD engine, but also we are embedding some dedicated hardware for the ciphering of the data. I show you right now some works that we have done in the past. So we can call them field demos. Okay, so these two machines that you see here on the screen are our initial demo units for some experiments that we have done in the past. We collaborated in the Metropolitan Area Network experiments already discussed and showed in the previous talks. But so that was the past, let's say. So speaking about what we are doing right now, we are working together with the CNR and INRIM and also NATO and the SPIN project. We are working on a underwater fiber link, 100-kilometer fiber link between Sicily in the extreme south of Italy and the Isle of Malta. So it will be the first undersea quantum key distribution fiber link between two different countries, at our knowledge. But coming back to what we have done in practice, we also made quite a funny activity. Let's say funny because it was a nice video call. You will see later in my slides. But here you see that it was essentially an activity based in the city of Trieste. It was it was done in the ending ceremony of the Ease of Congress 2020. So on 6th of September, we made this demonstration. We had Alice in the old harbor, old port of Trieste, and we had Bob in the main headquarters, in one of the offices in the headquarters of the University of Trieste. It was around 10 kilometers of fiber already installed, so we were using something that was installed in the city. And it was funny because we were making a video call between the former Prime Minister of Italy and the Magnifico Rettore of the Trieste University. So they were making the call, the video call with let's say, an announcement of security made by the sharing of the creation, sorry, of the quantum key, or the quantum keys by our instruments. Some technical details on that. The Alice system was performing a BB84 protocol, 3 states with time being encoding and 1 decoy state. From the Bob side, we can share with you that we used an auto-stabilized polarization independent fiber interferometer, and we were using standard InGaAs single photon detectors at the Bob unit. We had a running real-time key generation, but we were using 2048-bit for the encoding of the security of the video call. We were using 2 dark fibers, one dedicated to the quantum channel. During the experiment, we were in the round of 10 dB loss. We were using also another service channel based on another dark fiber. And also we were using essentially internet between Alice and Bob. So very, very common setup for the normal traffic. So here you see some shots of our experiment, some pictures. I would like to show that we were making this with the huge presence and collaboration of CNR and the Denmark Technical University. Again, it was quite interesting experiment where we were using our hardware and our QKD engine with them. So I finished my presentation quite early, I think. Here you have our main address. You can use my email to contact us. And just to say that we are in the process of hiring. So if someone of you is interested or have some friend that wants to make a job in this magnificent world, please contact us. Thank you very much.
So thank you very much, Dr. Tipinti. And here we can see that the quantum communication is boosting not just large companies, but also small and medium-sized companies and spin-off. And this is quite important, I think, also for the European quantum communication infrastructure and all the efforts that the European Commission is doing on this in this field. So now we can come back if Davide Marangona is now available for the talk. I don't see him here, and so I suggest to move to the next speaker who is waiting for the problems to be solved. So it is a pleasure to introduce the invited talk about quantum networks. So we are also enlarging a bit the topic of quantum communication to quantum communication, and we are coming back a bit to a research institute. The next speaker is Dr. Sebastian Tanzili from the Institut de Physique de Nice, CERNES, and the University of Côte d'Azur, France. So, Dr. Tanzili, the floor is yours.
Thank you, Chairman. Can you see my presentation?
Yes, we can see it, we can hear you well, and it's not full screen yet.
Yes, I'm trying to do it. I'm sorry. Yes, it is now.
Yeah.
Is it okay?
Perfect.
Okay, so thank you for having invited me to this workshop. As the chairman mentioned, I will probably go a step before from, I would say, the research laboratory side. And I will present to you today some block functions that my team has been working on over the past few years for building an operational quantum network compatible with telecommunication wavelengths. I will go gradually to the starting point of our research activities and tell you in more details about these building functions that we have carried out over time to finish by showing you the way we try to develop an actual operational quantum network in real field over the Côte d'Azur area, which is around the French Riviera in Nice. So the starting point of our, I would say, research activities has been this demonstration where we have made the demonstration of in-laboratory entanglement distribution over 150 kilometers in division in dense wavelengths demultiplexing environment. So we had a source. I don't know if you can see my pointer here, but we have a source composed of a laser and a periodically pole lithium niobate waveguide that emits over a very broad spectrum, pairs of entangled photons that are energy and time entangled. And we have had this idea to exploit the spectrum, the emitted spectrum, which is represented here, which is kind of a Gaussian function, I would say, and try to see whether we can separate this spectrum in two parts, apart from the degenerate point of the emitted spectrum, and having the exploitation of complementary channels that are compatible with telecommunication standards. And we have divided our spectrum in two bands of complementary channels made of 8 channels each on the 100 gigahertz DWDM grid. So you can see that energy time entanglement can be present and exploited in all pairs of complementary channel apart from the degenerate point of the spectrum, meaning that you can find entanglement in the blue-blue, in the green-green to the red-red complementary channels. So when the photons are emitted, the spectrum is divided into two. So the lower wavelengths are sent to Alice, which is here on the top, and the longer wavelengths are sent to Bob at the bottom of the slide. And energy time entanglement is analyzed using unbalanced Michelson interferometers that are homemade and well stabilized in terms of phase stability, I would say. And the two users are separated using 150 kilometers. So we have been able to demonstrate that energy time entanglement was preserved after 150 kilometers of separation of the pairs of photons. And we have shown that with equal photon pair emission statistics in the 8 paired channels that we have been exploiting, we have been able to multiply the key rate by a factor 8, which means that we have verified what we knew as a kind of a law that the key rates in quantum key distribution systems scales with n being the number of pairs of channels that you can exploit in your DWDM systems. After that, we have followed the way of augmenting the channel capacity, still using DWDM environment, but coding the quantum information on pairs of photons using hyper-entangled states. And in our case, it was energy time and polarization entanglement. So here's the way we have produced those hyper-entangled states. So we still have our same laser emitting at 780 nanometer wavelengths, and we have the same kind of PPN waveguide, which is now not in a single pass, but embedded kind of embedded in a Sagnac loop made of twisted polarization maintaining fibers. So in the clockwise direction, you can create the VV component of the polarization entangled state, and the counterclockwise direction, you can create the HH component of the polarization entangled state, such that you end up with an entangled state of the form HH plus VV, where you can manipulate the phase as well using your configuration, and the two photons are emitted at 1560 nanometer wavelengths. Knowing that this PPN waveguide is very, very efficient, the emission is very broadband in terms of spectrum, and that energy time entanglement is naturally available. So we had this trick of the Sagnac loop to produce the polarization entangled state while having naturally the energy time entanglement made available only by the nonlinear optical process. So here is the setup that we have been using. So you have here the source in the Sagnac configuration. And here you have two stages for entanglement analysis. The first one is energy time analyzers made as before with unbalanced Michelson interferometer, in which we can play with the phase thanks to a stabilization laser, which is not represented, followed by a polarization state, entangled state analyzers made of wave plates and polarization beam splitters. And we end up still with DWDM components that can separate our pairs of photons into 4 pairs of complementary channels, as I mentioned before, that are apart from the degenerate wavelengths of the emitted spectrum. So we have been able to verify that for all 4 pairs of complementary channels, we can violate the Bell inequalities with Bell parameters going up to 7.73, which is where the max violation can be 8 with hyper-entangled state. And for the first time, we have been able to provide a parallel analysis or simultaneous analysis of both the observable at the same time, meaning that we have been able to analyze energy time and polarization entanglement with a single setup, and violation of the Bell inequality has been made possible for the 5 complementary channels that we have been able to exploit. We also have another research line for a quantum communication purpose, which changes the technological platform from lithium niobate to silicon chip architectures. So here we have a silicon chip on which are integrated a ring resonator that has some resonances that you can exploit for signal and idler pairs of entangled photons, still energy time entanglement over the resonances of the ring resonator. And we also have integrated for the first time, together with the ring resonator, a series of 4 Bragg grading filters that are also integrated to reject the pump wavelengths on chip. So here it's not the second order nonlinearity that we exploit anymore, but this is the third order nonlinearity. So we start with a telecom laser, which is emitting at 1534 nanometer wavelengths. And you can see here the spectrum that we are able to process with such a chip. So here you have all the available resonances, the blue curve, that can be accessible by tuning the pump wavelengths. So you have a series of resonances that are exploitable, and we have exploited two pairs of complementary channels, so the blue and the red apart from the pump wavelengths, which means that you have entanglement in the blue for the blue idler and the blue signal, and for the red idler and the red signal apart from the pump wavelengths. And you can see here that the filter which is integrated on the chip, so the 4 Bragg grading filters that are integrated on the chip play their role, because we can see that we have more than 80 dB rejection of the pump wavelengths. So in the resonance of the pump wavelengths, we don't have any more signal, and we could not measure better, but we are pretty sure that we have almost 100 dB of rejection of this pump wavelengths. So we have made with 2 unbalanced Michelson interferometers that is represented here on this part of the slide, that we could see that we have a very nice entanglement visibility with row visibilities that are on the order of 97% for the 2 complementary channel wavelengths. We also have been working on generation of squeeze light, both using a fiber architecture and an on-chip architecture in collaboration with the Lens and Alessandro Zavata, who is online today. So here we have a telecom CW laser that is amplified, then separated into 2. The big portion of it is first frequency double, and then sent to a spontaneous parametric down conversion stage to generate single mode squeezing at back to the telecom wavelengths after the frequency doubling. And the smallest part of the intensity of the laser is used as a local oscillator, which can be controlled in phase and in polarization. Modes are recombined at the 50-50 beam splitter, so which means the single mode squeeze light generated in this PPLN device and the local oscillator. And we have been able to demonstrate that we have a very nice squeezing figure of about 2 dB. We also have made kind of the same type of experiment. So the setup is practically almost the same. We start with the same type of laser, but this time at another wavelength, which is 1560 nanometer compared to 1542 nanometer for the first experiment. So the laser is again separated into 2. The biggest part is frequency doubled, and then sent to a chip that integrates on a single substrate a PPLN waveguide section to generate the single mode squeezing, and a recombiner, which is a 50-50 coupler, which is also integrated on the chip. So this 50-50 coupler can make the interference of the local oscillator after phase control and of the generated squeeze light, and we detect this interference using a homodyne detection setup. And as before, we have been able to demonstrate that we have a nice figure of squeezing, which is of about 2 dB again. Another research area in which we have been working hard is a coherent frequency conversion for quantum memory applications and a priori compatibility. So we wanted this coherent frequency conversion to be polarization entanglement maintaining and be compatible with alkaline atomic based quantum memory systems such as rubidium and cesium species. So here we start with our Sagnac loop based polarization entangled photon pair source. So we have a laser at 780 which impinges a PPLN waveguide structure, and we emit polarization entanglement as before, as I discussed before, coded at the wavelength of 1560 nanometer. Then one photon is kept, the photons are separated, and one photon is kept untouched, and the other enters kind of a nonlinear Mach-Zehnder interferometer, which is composed of 2 PPLN waveguide structure, one for being able to convert the H component of the entangled state, and the other being responsible for the coherent frequency conversion of the V vertical component of the state. And this is made possible in the sum frequency generation nonlinear process, together with an escort laser pump at 1621 nanometer wavelengths. And with this, we have been able to demonstrate that we have very nice figures of polarization entanglement maintaining interference with raw visibilities that exceed 95% when we make the measurement of the polarization with polarization analyzers with the photon at 1560 nanometer that has been untouched, and the newly, I would say, frequency converted photons from 1560 nanometer to 795 nanometer wavelengths. So 795 nanometer wavelengths is a very interesting wavelength, because it can answer to all quantum memory systems that are based on either room temperature atomic vapors made with rubidium, or cold atom-based quantum memory systems, because the wavelength remains the same, and it is for the D1 line of the rubidium species target. The target wavelength is 795 nanometer wavelengths. Another very interesting
sorry, 2 minutes.
Yes, I'm done. It's my last slide. So the last point that I would like to discuss today is a very interesting plug and play way of synchronizing the nodes of a quantum communication networks using a master optical clock in a quantum relay configuration, where pairs of photons, where you can see on this picture that you can have local fiber area quantum networks, and that you can distribute master optical clock to all those nodes and generate photon pairs or single photon states that are all paced using the same master optical clock. And we have tested this approach using entangled photon pair sources that are gradually separated in terms of distance between the two. And we have materialized or measured the way or the precision with which we can synchronize the two sources using the initial master clock, using Hong-Wu and Mendel effect made available at this beam splitter. And you can see that the Mendel deep visibilities from 10 meters to 400 meters to 100 kilometers separation between the two sources exceeds always as a lower bound 95% visibility. So with all those building block functions, we are now developing our own fiber-made or fiber-based local area quantum network over the Côte d'Azur, which is a network that spreads over 30 kilometers with the help of the provider Orange, which provides us the fibers with which we establish our quantum network experiments. And our long-term vision is to connect colleagues from Paris and Grenoble, Paris and Nice, using a source of pairs of photon that should be embarked on a satellite as a quantum payload. I thank you very much for your attention, and you can see here all the papers that I have been discussing today during my talk.
So thank you very much also for the quantum networks perspective that have been presented. And in the meanwhile, also Davide Marangon has been able to properly connect.
Yeah,
perfect.
Really, thanks. I do apologize for this problem, and now I'm connected with my mobile data, so I prefer to not to keep the video feed off in order to have more bandwidth.
Okay. So we step back to a company presentation, and here we are going to listen about another very relevant topic like quantum random number generators. So please, Dr. Marangon, the floor is yours.
Thank you very much. So my name is Davide Marangon, and I'm a research scientist at the Cambridge laboratories of Toshiba Europe. My presentation will be divided into two parts. First, I will give a brief overview of our quantum random number generator, and then I'll briefly talk about long-term perspective and assurance of quantum random number generators. So, the quantum information group at Toshiba Europe is based in Cambridge, where we research and develop technologies for quantum information. In particular, we develop systems for quantum key distribution and quantum devices, such as a source of entangled light and single photon detectors. For quantum cryptography, besides the research on quantum key distribution systems, we also develop quantum random number generators. So this is really a flashlight about all the recipes that we explored during the last years that range from discrete to continuous variable generation protocols. Our main favorite mechanism now for generating random numbers is based on laser spontaneous emission noise, which now I'm going to give a brief introduction here. So, the source of randomness of our system is a laser diode that we modulate with a current signal below and above its lasing threshold. In this way, we generate optical pulses which all have the same amplitude, but a random phase. Why is it so? Because the physical preconditions before the generation of a new pulse are two. One is that current is below threshold. Second is that there are no coherent field inside the cavity. In this way, the laser is generating photons by spontaneous emission from the interaction with the cavity vacuum state. These spontaneous emitted photons then acquire the phase of the vacuum state, which is undefined, which means that it's uniformly distributed between 0 and 2 pi. Now, when the current steps above threshold, the spontaneous emitted photons trigger the emission of the coherent pulses and transfer onto them the random phase of the vacuum field. So now we established that we have optical pulses with random phase. How do we get the random numbers? We plug the laser into an interferometer, which interferes consecutive pulses by splitting and delaying 1/2 the pulse with respect to the other. And in this way, at the output of the interferometer, we obtain pulses that now have a random intensity. Then these random optical pulses with random intensities are converted into a signal, a current signal with random voltage, which is digitized by an analog to digital converter. And in this way, we generate the so-called raw random numbers. Here, in this plot at the bottom of the slide, you can see the distribution of the intensities. They are not uniformly distributed, but they follow a so-called arcsine distribution. The distribution is the result of the interference law. So the important point here is that when we witness this distribution, well, this is the signature that our system is following the theoretical model for the spontaneous emission, for the phase randomization due to spontaneous emitted photons. The nice thing of this generation scheme is that it's very simple, and one can build a quantum random number generator using components for optical communication, which have two very positive aspects. The first is that they are commercially available and can be, and they are indeed known as shared products. The second one is that these components for optical communication can be modulated at very high rates. So here I'm displaying our integrated prototype. The optical core is indeed built with a 1550 nanometer fiber coupled distributed feedback laser, a fiber interferometer, and a wideband photodiode, all optical components for telecom communication. This optical core is then assembled on a single printed circuit board together with all the supporting electronics for fast sampling and processing. And we clock the system at 1 GHz. In this way, we obtain a maximum output rate up to 8 gigabit per second. Obviously, as I showed before, the raw random numbers are not uniformly distributed, so we implement a fast processing algorithm that makes the numbers uniform. Besides that, another interesting feature of our system is that it has monitor functions that allows the user to keep under control the physical parameters of the system in order to understand if everything is running smoothly or if some other parameter is drifting. For example, let's say the power of the laser. In this work that is referenced here, we we present the results of a continuous testing for 70 days without interruption. While the generator was outputting the number, at the same time we were testing them. We were testing the numbers with very stringent statistical tests, and all the tests were passed. So now I'll move towards the second part of the presentation. I will talk about long-term perspective and assurance of credentials. Now, having a system, a quantum random generator with a clear and sound physical model, and which passes all the tests, is obviously a strong starting point. But in terms of long-term commercial perspective, it would be even better to have some industrial standards to show the user that your quantum random generator is complying with. Currently, do exist and are well established standards, industrial standards for pseudo and hardware classical random number generator, such as the NIST one from the National Institute for Standard Technology in the United States, BSI one that is the same thing but for Germany, or the ISO one. Concerning instead quantum random generator, there are not currently any kind of standards, and there are not even groups that are working in preparing standards. For example, for the QKD, there is the industry specification group of ETSI, of which for example, is the chair. But for quantum random generator, there is nothing. And this is somehow, relevant, because now I'm going to think it's interesting to introduce here the official position of the National Cybersecurity Center, which is a British institution that monitor all the cyber infrastructure of the United Kingdom. Last year, they presented a white paper on quantum technologies, and the official position of the NCIC about quantum random generator is that they believe that classical random number generators will continue to meet their needs for government and military application for the foreseeable future. But for quantum random generator, they just say that they will continue to support the research. So, which are the critical points that have made the NCS take this position? Well, there are two things here. The first is that, as they say, the unpredictability of the number is difficult to assure, because as the random number generator, the quantum system sits on a classical system, gets inevitably contaminated by classical noise. The second point is that, again, as the quantum system sits on a classical electronic system, it can be attacked by an attacker, not only for what concerns the quantum side, but also for its classical side. So, to sum it up, in principle, quantum random generator output unpredictable randomness, but it's still hard to assure that it's just a randomness of quantum origin. And it's clear then that at this point there is a gap of trust between the well-established classical random number generators and the quantum ones. In this context, it's worth reporting that within the EuroQCI initiative for quantum technologies, 2.8 million pounds were recently awarded to a consortium of academic and industrial partners to specifically address the problem of current assurance. The consortium is led by the National Physics Laboratory, and FIBA Europe is one of the partners. Also, CAT, for this talk, is another industry partner. Here, you can see all the companies listed at the second bullet point are just, companies that are now actively researching into quantum random generators. So this clearly shows that there is a huge interest in this kind of technology, and hopefully, really, this project will be able to boost the commercial industrial potential for quantum random generators. Within this kind of research, now I'm going to present one of our fresh results. So we are interested in understanding what can be the vulnerabilities, the classical vulnerabilities of random number generators. So a very popular and common architecture for quantum random generator is the one based on the so-called homodyne detection scheme, which I'm showing here. With respect for them to the previous one that I showed, it's based on a continuous wave operated laser. So here we are not pulsing. And it's more or less self-explanatory. So the combination of the current signal output by two balanced detectors, the homodyne configuration, is sampled, and according to the level of the current output by the detector, if this current signal is above a given threshold, you can get a bit 1. For example, if it's below the threshold, you can get the bit 0. The nice, interesting thing about this scheme is that it's very simple, it's very popular, and the vast majority of the last papers about this kind of generator, they all use the same kind of detector, a commercially available detector that it's sold already shielded against electromagnetic interference. We used this detector in the past, and we discovered that it has, despite the shielding, a sensitivity to external electromagnetic fields. So we ask ourselves, can the detector sensitivity be exploited as a side channel for an attack? The answer was yes, because we did this experiment. We took an antenna and we used it to emit a radio frequency interfering signal that was affecting the current signal in output from the detector. And as you can see, what you have is that now, if you are able to synchronize your interfering signal with the sampling rate of the digitizer, you can shift, as you prefer, the level of the current, and therefore impose your deterministic output on the random number generator. And we were able indeed to influence the output of the generator with high confidence and with high success confidence. So this is an example. This is just an example of how a system, okay, it's a quantum system, so you are supposing to have unpredictable numbers, but still there can be side channels, classical side channel, like in this case, that can be exploited by a potential attacker to make your numbers predictable and any more secure. So, well, these results will be soon appear on Physical Review Applied. To conclude, random generator based on spontaneous emission noise is a strong and effective way to produce random numbers. It's so simple to implement with telecom components, but it offers also a lot. I mean, it's a pretty remarkable as it's scalable. In fact, we were able to reproduce the same kind of protocol using an integrated photonic chip on indium phosphide heterostructures. And in this figure here, you can see, for example, a 2 by 6 millimeter square chip where we are interfering the signal emitted by to gain switch the laser. So in this case, we do not have anymore the interferometer, where we have two lasers that are emitting phase randomized pulse independently. We interfere the two pulses, and in the end we get the same arc sign distribution that I showed you before. And so inside this battlefield, inside the battlefield package that is depicted on the right, there are, I mean, we have packaged this system, and it's two lasers, photodiode, so a complete optical core that is scaled, that has a factor 100 of reduction with respect to the previous one that I showed you, realized with discrete components. Second thing, for the future widespread comparison exploitation of coherent random generator, reference criteria for the assurance of the device are of critical importance. And for this purpose, research has not to be limited only on the quantum aspects of your system, but it has also to explore and analyze deeply what are the classical possible side channel of an actual implementation. So that's all, and thank you.
So thank you very much, Dr. Marangon, and we are on time. So I would like really to thank all the speakers for this quite complete, relevant, and interesting landscape on the ground segment of the possibilities for the European quantum communication infrastructure. Thank you very much. So I think the session ground segment is concluded now. So I think that I can give back the stage to Francesco Cataliotti.
Thank you, David. I was trying to find out. Okay. We are actually supposed to start with the second session and chaired by Davide Bacco. So, Davide, I've seen you. Exactly. I don't know if, yeah, it's yours. If we want to make a couple of minutes of maybe.
Yeah, I think it's with the mindset at least, I mean, a couple of minutes of break. So let's start in 2 minutes. So, okay, here we are back. So welcome everybody to the second segment, that is the space segment related to the European Quantum Communication Infrastructure Workshop. And in the second part, we will listen to 3 talks, 1 tutorial and 2 invited talks. So let me already start by introducing Dr. Rupert Ursim from EuroQCI, the Institute of Quantum Optics and Quantum Information in Vienna. And please, you're welcome. The stage is yours.
Thank you very much. Can you somehow allow me to share my screen?
Yes, I guess it's Alberto, right? You should be able now to share your screen.
No, I was a second ago, I was able to do so, but now it's it's not.
What about now?
No. Ah, yes, now.
Okay. We can see your slide.
So it should be
Yeah.
so okay.
Perfect.
So thank you very much for giving me the opportunity to speak. I would like to introduce a little bit on the work we have performed in Vienna and give you some insights into our know-how we gained over the past years doing free space experiments on Earth, terrestrial, as well as also with spacecrafts. So first of all, I would like to introduce you to the question, so why at all we want to go into space? It was actually Jonathan Dowling, who unfortunately passed away a couple of months ago, who performed this, I think, the most complete feasibility study on comparison of the ground segment, speaking about fibers, as well as the space segment, speaking about satellites. And as you can see on the right-hand side, you need quite a huge number of quantum memories being available to the network in order to bridge distances you can easily bridge with satellites, being at the altitudes of a couple of 100 kilometers or even higher. You can easily see that you can bridge Europe to US distances quite easily with satellite, not with just LEO satellites in 100, 500, 600 kilometer orbit, but a few thousand kilometer orbit would already do so. There is an optimum there. There is a trade-off there. So going into a geostationary orbit might not be the best choice because of the 40,000 kilometers you have to bridge. The most simple way of doing those kind of implementations would be a quantum key relay demonstration. A quantum key relay where a single satellite is used to distribute to two different ground stations, which are not simultaneously in the field of view. So you can do entanglement-based quantum cryptography. But here we assume two ground stations on opposite side of the Earth, where you can distribute still a secret key, assuming the classical, so to say, the classical memory on the satellite is secure. So you distribute it to one ground station, and then you distribute the second key to the second ground station. And as you all know, this we call a trusted node. So this is more or less the most feasible thing, and according to the plans I know so far from the European Commission and also from the European Space Agency, this will be the first implementation here in Europe. So we as a group, we have gained most of our know-how not in Austria, funnily enough, but in the Atlantic Ocean. We don't have an ocean in Austria, so we like to go to an ocean. I will speak about a second experiment in a few minutes, where we connect two islands, La Palma and Tenerife, where we did like 10 years ago, more than 10 years ago already, a so-called BB84 experiment together with Harald Weinfurter from Munich and John Rarity from Bristol. So we used a BB84 system, decoy sources, decoy protocol have not been invented at that time. So this was an unsecure implementation, but nevertheless, the principle is the same thing. So we switch the polarizations by switching on and off 4 different laser sources, and we transmit over that 144 kilometer link, which corresponds to minus 30 dB, pretty similar to a downlink from a satellite. And on the other side, we used an optical ground station provided by the European Space Agency, 1 meter in diameter, you can see here, where we tracked these laser, this beacon laser, and we measured this with single photon detectors, time tagged them, synchronized them to GPS. So it's a GPS stabilized system in time. So we can associate the sent and the received photons. Second, I would like to mention also an experiment we did together with the Chinese Academy of Sciences, Professor Qianbai Pan. They launched a satellite in 2016, and not many people know that the Chinese launched actually 2 satellites in 2016. This was Meteos, which was in the public media. There's also a second mission called in Tiangong 2. So there are only scientific papers because the public relation was not made that well. But Meteos, which I will talk about here, is a sun-synchronous orbit. So it always its inclination is 97 degrees, 500 kilometers height. So it always passes paging at midnight. So you have every night 1, 2, sometimes 3 passes overhead. The satellite is equipped with a BP-84 decoy source. Decoy was invented in 2016 actually by the Chinese. And also what is not mentioned here in an entangled photon source. You see here on the right hand side a telescope, and here is a big aperture for uplink as well as for downlink experiments. So this is Meteos. Meteos is a square meter huge satellite, and it also equipped with a beacon synchronization equipment. So the satellite also had 4 laser diodes, in fact 8 laser diodes to switch between the decoy and the signal pulses that were combined in free space with these polarizing beam splitters, as you can see here. Then there you see the telescope, the alignment laser for the local system, as well as the 532 nanometer synchronization laser. This is actually the laser you see when the satellite points towards you. I will show you in a second. On the ground, we as well as our Chinese friends use the telescope to collect that light. So no real optical quality is required, but you just collect the photons on the single photon detectors, SPD1 to 4 here. And this is how we did, and the Chinese did the downlink from the Meteos satellite. So we used a 50 centimeter telescope located south of Vienna. You see the white telescope is built for laser ranging, and the black stuff here is our quantum receiver. You can actually see these accelerators, the green stripes, so that these are the 4 detectors with the time taker and the computer. So we compensate for all the atmospheric fluctuations passively. So the field of view is designed in such a way that this can handle the fluctuations. It is very close to the city center actually. So we had also to shield the street lights. It was very close to the airport, so we had to fight with aviation safety control in Austria, which was, by the way, the hardest part in that experiment. So you see here, unfortunately, a very bad picture, but couldn't find anything better. But you see, it's quite a big implementation to compensate exactly for these deviations from the atmosphere. So here again, you see the beacon laser. The beacon laser is sent up to the satellite such that the satellite can track the ground station. You see here the green light which comes down from the satellite to track it, and then the satellite light from the beacon is split away with this dichroic mirror, and here's the detection module, as you all know. And these are actual data. You see in the bottom the Meteos, MOZI, as the Chinese call them, the MOZI elevation angle. So this was not right through the zenith, which you can anyway not do with this telescope because this had a singularity in the zenith. So plus 80 degree. And here you see X and Y differences from the set point. So if we switch off the beacon, we easily lose the link because of the mispointing of the satellite. And then you see here the fine pointing of the closed loop with the telescope. So here you see actually the synchronization pulse. So the synchronization is a very strong laser on the satellite. It emits with a little bit more than 10 hertz, kilohertz. You see here it's above the 10,000 counts per second. So this is for timing synchronization of the send and receive photon. And the others are the 4 polarizations. And you see there are some clouds at the beginning, and the full link duration is approximately I don't know, like 200, 250, sometimes 300 seconds. So this is the distance of the satellite, and then we can from the receiver, and then we can distill a shifted key rate and also a Kuber from the satellite. So here, this is the publication we did together with the Chinese Academy of Sciences. So 3 ground stations, 2 in China and 1 in Austria, were involved at that time. And we did several links on several days, as you can see. And our data rates, I would like to mention, are not as bad as expected. Consider that we only have a 50 centimeter telescope. The next experiment, which is also insightful, I just want to mention it, is also something we Austrians did in the ocean, this time in the Mediterranean Sea, between also 2 islands, namely Malta and Sicily. We had Kalonikov, who is in the audience, as a partner to do this this experiment. So we also had this is a telecom source. We had a PPLN telecom source, which was locally detected by a nanowire, and then we sent it over this 100-kilometer long link to Italy, and we synchronized again using GPS clocks. We were not able to actually distill the key. That implementation we did in a second publication I will not present, but the coincidence rate was a few hundred hertz. So the secret key rate would be about 30 hertz. So this is very much in the region where EuroQCI will be at the end, because this is the state-of-the-art technology to be used. So we do a few experiments of these already in Vienna. We try to span out not only to our neighbors, but also to Poland. So Vienna is quite a fortunate situation, because the borders are really close. The distance between Vienna and Bratislava is only 70 kilometers. It's the second closest capital cities in the world. The closest I found later out is Vatican and Rome. I think you cannot beat that. You cannot minimize the distance between capital cities. And we will now span out also to the south, to Slovenia and Italy, Trieste, and even further to Tuscany, to Alessandro and Samata. So we also use for that experiment entangled photon sources operating at telecom wavelength. So we do quite a few experiments now. I would call that quantum communication 2.0, which is a fundamentally interesting thing to do. We try to get rid of noise counts. We try to do purification experiments on a long distance link. You see here a single photon CNOT gate, where we use 2 different degrees of freedom to purify our quantum state over longer distances, which will be important for achieving longer distances. Here we do high-dimensional EPR entanglement from SPDC at telecom wavelengths, exploiting the path degree of freedom. The third one is exploiting wavelength division multiplexing using entangled photon sources. As you can see, you can drastically increase the count rate over longer links using such a well-established technology. And I think this will be very important for EuroQCI. We did that in the laboratory, and soon we will also publish that on a deployed link. And last but not least, we did also hyper entanglement experiments using time energy entanglement as well as polarization entanglement. And the advantage is that if you go to higher dimensions, you can work at huge background noises. And this has two advantages. First of all, you can work with cheaper detectors, which is maybe a technological argument. But second, you can, in the presence of any dark count, reach longer distances, because the distance limit is only dark count and in these experiments. So the loss in the detector and the loss in the link is something you can beat with just the integration time. But the actual wall you bump into if you want to reach longer distances is only limited by the dark count. So this is one way of solving that issue. Of course, I should mention here that having lower loss and high detection efficiency gives you more secret key rates, which is quite important for a customer who is actually implementing stuff. I would also like to mention that we are doing quantum networks, not only in the laboratory, which we published in Nature 2 years ago, but also we did it now together with my former postdoc, Siddharth, in Bristol. We did it on a deployed fibre network. 16 receivers have been deployed throughout the city, and with only one entangled photon source you can see here, and the full, not the full, but a huge spectrum exploited by wavelength division multiplexing and cleverly arranging things such that you have only one fiber to each of the 8 receivers, 16 receivers in the latest application. We were able to make a network which scales very similar to a classical network, where you also have only one fiber or one connection to each other, and not everyone has to everyone a connection. So in that sense, it's a fully connected network, the most general way of distributing entangled photon sources to people. Last but not least, I would like to mention that we funded a company in Vienna, and I would like to introduce you very briefly to this company. The company is doing space QKD and terrestrial QKD. We do consulting to companies, to governments who are planning to implement QKD networks. We are also active already in EuroQCI projects. For the European Commission and also for the European Space Agency, we do prototyping, also for venture capitalists who are now engaging and being very active in that direction. We produce, we won a contract for the European Space Agency where we produce an entangled photon source which gives 2 orders of magnitude higher bit rate compared to what is currently published in the literature. This source will be necessary to bridge long distances from a satellite using entangled photon sources. We also want to mention that one of our goals is to be the manufacturer of an optical ground station infrastructure together with our partner in Austria. This telescope you see here is an 80 centimeter telescope, also a 40 centimeter telescope is available, and we believe we can meet a very low target cost price to deliver an optical ground station. The optical ground station includes not only the telescope, but also the quantum, the classical receiver for the classical communication channel, the dome, and the full infrastructure required to set up such a a telescope on the rooftop of a bank, for example, in the city center in any city. I would like to mention that this is a telescope we actually used for our telescope experiment together with the Chinese Academy of Sciences, and it was already quite successful doing so. So last but not least, I seem to be a bit faster than I had planned. Last but not least, I would like to make some advertisement that we are hiring this time. So if you know a gifted young student who would like to work in a company, startup company, please let him know that we have a laboratory and a very nice working environment. And with this, I would like to conclude. Thank you very much. If there will be some questions, I would be delighted to answer.
Thank you. Thank you a lot, Rupert. It was a very nice overview of all the activities that you're doing in Vienna. I'm also very happy to see that there is also a new startup that is coming there. I think we are actually just on time, and similarly to the previous session, we would like to keep the question and answers for the Slack channel, and we can just move to the second talk of this session.
Sure.
Thanks a lot again.
Thank you.
Let me introduce Alan Kurozevich from SES.com, and Alan, the stage is yours.
Thank you very much. Thank you, David. I think I couldn't have a better introduction to my presentation than I had from the Rupert, because he really put everything, laid down what I'm going to talk about in the matter of implementation for the commercial service for the future. Let me see if you see my presentation. Let me try to share the screen. Do you see it?
Yes, that's perfect.
Okay, thank you very much. So yeah, so I'm going to give in the next 50 minutes just a very high level overview of basically who is SES in the first, because we might not be very well known among the cyber, let's say, companies or cyber ecosystem, and then give a little bit more introduction on the let's say what we believe is the most advanced and definitely first to come space-based implementation of the quantum key distribution. Everything okay? Yes. Quantum key distribution to be launched in a few years from now, and how this actually fits into the complete EuroQCI ecosystem and the projects. So coming back to the first slides, SES is actually the world's biggest satellite operator. Our history dates back in 1985. And we started with let's say, direct-to-home TV. Today we are the more network company. Then obviously TV is still big business for us, but we are moving gradually to the networking world, to the telecommunication provider role, with a series of acquisition, a series of technology developments. We currently run the fleet of 74 satellites. We are the only satellite provider in the world that actually operates multi-constellation or multi-orbit constellation. So we operate geostationary satellites and medium orbit satellites. And we're covering almost 100% of the world's population with our satellites. So we are headquartered in Luxembourg, but our office is all the way around the world. And we are currently about a little bit more than 2,000 employees. We also run the complete ground infrastructure with lots of fibre and other type of terrestrial communication in order to complete, let's say, our space infrastructure, which is very important also because it's as such we can provide a dedicated end-to-end service to our customers wherever they are in the world, being through the satellite or through the terrestrial combination of satellite and terrestrial network. Just maybe about ITASEC21, I'm personally the managing director of ITASEC21, which is the 100% owned unit of SES, which is dedicated to the mid-long-term technology developments. And obviously, quantum key distribution is one of the topics we are addressing here. And it's a company who actually leads this on behalf of SES group together with a cooperation with ESA and European Commission. So why we actually have a quite history of space innovation. We have been the first space company to run the electric propulsion, first to launch with SpaceX. We are launched also first satellites with the fully software-based processing. And of course, the quantum key is just one kind of example of this innovation that we are putting in space today. When we talk about the quantum key distribution from the space, obviously we're all aware of the quantum threats to cybersecurity. I think the whole day today and the days to come in this conference are really dedicated to the subject. I'm not going to spend much time on this, but one thing that I would like to kind of stress here is that fact that advanced of the quantum computers is not only threat for future, it's definitely threat for today, because we're not talking about only the real-time communication in the future, but also all the data information that are stored today are going to be vulnerable in the future when we have the quantum computers. So all the attacks of the type of intercept now and decipher later are possible. And for that reason, I think we are already probably a little bit late with making sure that we are quantum resistant for the future to come. Now, what is the role of the satellite in the quantum key distribution? I think we all know that the whole premise of quantum key distribution is to address the topic of, let's say, public-private key deficiencies in the area of quantum computers. And if you look at this, let's say, opportunity, the quantum key distribution addresses a small segment of the complete, let's say, encryption of the data and the communication network, which is how to efficiently distribute the symmetric keys to the system and potentially use the existing symmetric encryption algorithms to have information theoretically secure system that cannot be that provenly cannot be broken by the mathematical means we know today and the computer power that is going to come into the future. Obviously, quantum key distribution is one, let's say, possible solution, and the solution that is the only solution today which is theoretically unquestioned. And but it lacks from the fact that the quantum key distribution can be done on a very limited distance over the fiber network. And in that respect, the satellite plays a major role here to bridge these distances on a larger global or regional scale. So as such, basically, we will be able to move the current limitations of about 100 kilometers to distribute the quantum keys to the much wider distances, as also presented by Rupert in the presentation just before. So maybe just a few words about the Quartz. Quartz is our current space-based quantum key distribution program. We started that in the late 2018, which is basically Quartz is the program to show the complete end-to-end distribution of quantum keys using the satellite technology. It obviously addresses certain technology challenges, but it's not only to prove technology, it's really to prove and demonstrate complete end-to-end service to the end users. So the current Quartz program is going to end up, it's a program basically funded by European Space Agency, and it's going to end up later this year with a basically payload proof of concept and a complete end-to-end system being implemented, however, without the flying satellite. It's going to be on ground proof of concept, which we plan to extend in the next phase, what we call here Eagle 1, with the first satellite to be flying the technology developed inside the Quartz program. and improves as a result of the lessons learned from the Quartz project. And the current Quartz consortium is basically, let's say, creme of the European quantum and space industry. Everybody who has work on this is part of the consortium and has significantly contributed to the making the Quartz not only end-to-end, let's say, complete system service delivery, but also making sure that the most, with the very few exception, technologies in the Quartz are coming from the European partners, and as such also contribute to the sovereignty of European solutions in terms of the cybersecurity. While we were doing the Quartz, in the meantime, obviously, European Commission came with the EuroQCI initiative. I'm not going to spend much time here on that, because probably speakers before have been addressing this before. EuroQCI is a network of networks composed of the basically ground and the space component, and the interfaces to interface the key distribution between ground and space. And here we position ourselves as a satellite operator as a first contributing mission to the EuroQCI through the program which is currently known as Eagle-1, which is going to be the first end-to-end quantum key demonstration, in-orbit quantum key demonstration, slated to be launched in 2024, and then operated for a few years, and followed up by the potential constellation of satellites, between 5 and 7 satellites, LEO satellites, to be forming the first, let's say, commercial constellation of the satellites to provide the QK, space-based QKD system. So what is the Eagle-1? It's based on the Quartz developments. It's a LEO system based on the prepare and measure protocol. We believe today, with the current state of technology, it's probably the safest way or best way to implement the quantum key distribution system from the space. We're using onboard quantum key generators, which makes the satellite a trusted node. And we are looking here at the complete end-to-end system. So basically to the complete delivery of the keys to the end users and integrating those keys into existing commercial and government-owned communication networks. So the project also looks at the developing of the optical space terminals, both on the satellite part as well on the ground terminal. Our partner for the space terminals is going to be TSAT. It's a German company, very well known into the optical space equipment. We are going to use a 155 nanometers wavelength technology. And we are going to also implement all the software elements that come on the top, both on the ground and on the satellite, to make sure that the whole protocols required are basically carefully implemented in line with the latest security needs. And they basically, as such, composed end-to-end service delivery, the system to be demonstrated to the end customers and potentially institutional customers. We are looking at the Eagle-1 as the first contributing mission to European Commission, to the EuroQCI. And the Eagle-1 is going to be developed jointly with ESA, European Commission, and being led by SES and the partners in the consortium. Maybe also just how this actually fits into the maybe national programs, because as a part of EuroQCI, you know that there are a number of member states' national programs, with the example of Luxembourg, for instance, where we are based. Obviously, the idea here is that each national QCI infrastructure is interlinked using the Eagle-1 satellite, so that nations are connected and can interchange keys using the space-based quantum key distribution. And also addressing the cross-border cooperation as a part of EuroQCI. As a part of our activities in Luxembourg, we have already engaged with Italy, Malta, Croatia, Greece, and neighboring countries like Netherlands and Belgium to make a small consortium to actually work on the interconnectivity between space and terrestrial, and cross-border key exchange between the let's say, neighboring countries, but also the countries which are a little bit far away using the satellite-based quantum key distribution. So that's short from my side. I'm open for any question. Thank you.
Thank you, Alan, for a very nice presentation and for being on time. So actually, since we have a couple of minutes more, I take the opportunity to ask the question on this. And let's say that is a more general question, but most of the scenario that we have seen in the last two talks are considering a kind of a downlink scenario, right? Can you explain a little bit about why these, and can you give some more insights about this choice, or what do you think? What is your opinion on this topic, Alan?
Yeah, absolutely. I think when you say downlink scenario, I guess you assume prepare and measure scenario in which you have a trusted node in the satellite, as opposed to the entanglement scenario, which you have. Yeah, the reason is following. It's first of all, with entanglement scenario, there are multiple reasons. Like entanglement scenarios, you have to cover, let's say, you have to have simultaneous visibility of two sites at the same time in order to share basically the key. So basically, they have to be connected, if you want to call it, to the satellite at the same time. That means the satellite footprint has to cover those. So you can not actually, let's say, connect sites which are further than 1/3 of the, let's say, Earth surface, because just for the, let's say, physics of the satellites. And the second thing is like that. Also, the quantum is all about the very low energy signals. It's and the more you go up in order to increase your coverage, if you want to call it, or distance between the sites, obviously you have more problems with the making sure that you get a reliable communication between satellite and the ground, because your link budget doesn't close. We all know that in the current state of technology, you have to do it during the night. There has to be no clouds. So if you really want to do it reliably and something that has commercial sense, I think prepared measure is probably the best solution today, because you will have, let's say, first you will be able to connect any two sites in the world, and any two sites that doesn't have to have a good weather at the same time and doesn't in the same footprint on the satellite at the same time, which makes it, let's say, as a use case, a potential application much wider than actually the entanglement case we have as a kind of alternative.
Yeah, makes sense. Thanks again. Thanks, Alan.
Thank you.
Okay, so let's move to the last talk of the session. It's a pleasure to present Professor Paolo Villoresi from the University of Padova, and he's going to talk about advances in quantum communication. Paolo, please, the stage is yours.
Thank you very much, Davide. Can you see the slide?
Yes, no. A little bit small.
I see. So we can put in like this.
Yeah.
Okay. So good afternoon, everyone. I'm glad. I would like to thank the organizer for the invitation, and also I'm glad to see that ITASEC actually expanded very much in the quantum security in these years. That attest essentially the interest in this domain that is essentially shared with you. In particular, you issued this very strong statement: the future is quantum for the ultra-secure communication network. And in my talk, we'll start underlying that this EuroQCI initiative is indeed aiming to protect our economy and society from cyber threats. And it is a combination of terrestrial space implementation. So we have to keep in mind of this interplay of space and ground parts, okay, and the early users that are government agencies and authorities, and then the private industry, the banks, institutions on regional scale, and at the end services. Okay, so because of the size of Europe, because it has islands, of course, satellites provides the optimal solution to cover these large territories and to connect the regional networks. Okay, it takes indeed the organization of this in the sharing of the keys in different type of protocols. So about the road mapping of this, how to get there. Since many years, the academic and industrial community in Europe envisage the paths that are effective to get to this real picture. Okay, I had the pleasure to also help in putting this together at the beginning of this phase that essentially converged in 2019 on a roadmap that was essentially distilled and is actually presently still available within the cost action QT space. And we have the pleasure to have the coordinator, Professor Bassi from Trieste here. After that, essentially, you can see that the steps are essentially looking at the first, the most effective demonstration that is based on prepare and measure QKD from low Earth orbit satellites, then to enable essentially the transfer of key on ground, the interchange with the satellites, and then go with higher and higher orbits toward the MEO, and finally embrace the entanglement distribution in the final phase of this the development. Of course, this takes resources, and after the ministerial meeting of November 2019, essentially the resources were found, the funds are available for the development up to the in-orbit demonstrations. So you of course need to say address this endeavor of going to space with quantum communication by looking at the different problems. Okay, and I would like to say go along these points, also mentioning the work we have done. Okay, we have of course already had the introduction to these things, but essentially when you actually have to think of a satellite that have to do quantum communication, well, you have many variables, and these are the one on the left. So you have to choose the altitude, the path, the path, say accuracy, the size of telescopes and space on ground, the location. Of course, meteo is something that comes to play, and then the type of protocol to choose, the clock rate, how to reject the background, and this allows you to get to the key rate. And thanks to the duration of the passage, you get a number of secure bits with telescope A, and then you reproduce this on B and C and D. So where are the steps that I needed to check? First of all, there is the exchange, possibility of exchanging photons from space. This was an open issue at the beginning of the millennium, and we enjoyed the hospitality of the Italian Space Agency in this wonderful location of Matera for pursuing actually the first experiment in this direction. Thanks to the big telescope you see on the bottom left there, we were able to demonstrate that actually you can actually create a quantum channel between space and Earth, and as was mentioned in the physics world, quantum communication via satellite might be soon feasible in 2008. Okay, despite of the strong attenuation, we were able to essentially create a source of single photon in space using retroreflectors that were launching on the ground at the single photon level, the photon that were suitably received on ground. This test was first done in LEO, then it was extended to MEO, to 7,000 kilometers 5 years ago, and eventually to the very crucial satellite altitude of 20,000 kilometers. That is where the essentially GNSS like Galileo or GLONASS or GPS constellation are located. So it's very strategic. So no problems in this single photon exchange, and then you have to encode. So, you know, light has many modes, polarization, temporal modes, also OM, okay, which is not very much feasible for this type of length of the links, okay. The first things we've used was polarization. So using qubit coding in polarization. We were able to show the first ever quantum communication from space in an experiment done in 2014. And here you can also recognize our chair and how we got into the trade, where we essentially had the different qubits that were essentially back reflected down at single photon level from the satellite and correctly detected on ground, again, by the telescope in Matera. Another degree of freedom was time, and essentially using temporal modes and what are known as time bin, okay? We were able to encode essentially a phase information that is related to the satellite velocity, and with that essentially create, using an unbalanced interferometer, the peaks that attest the constructive and destructive interference in the case of a different position of the satellites at different value of the relative velocity. This was repeated for a number of satellites, attesting the possibility of using also this degree of freedom for the encoding of information, of quantum information, essentially, in the space channels. These two degrees of freedom can also be combined, okay? And this is used when you have to go forward and also expand a larger Hilbert space, or just to do something more complicated. We use this possibility of combination in a fundamental test that is the wave-particle duality, done for the first time in space. The famous Gedanken experiment of John Wheeler of the delayed choice, where we essentially choose which type of measurement, if we are measuring a particle or a wave, just at the last moment after the particle has entered our instrument, according to his Gedanken experiment. So in our case, we were using the time to switch about different value of phase and the polarization to decide which type of measurements, okay? So in our experiment, essentially, we were investigating whether we are looking at a particle, and so which path this particle was chosen, or a wave, and to see the interference of it, so the visibility of the interference. And the results have shown that if you are actually aiming at the which way, so the particle-like behavior, we found a visibility of 95%, and so only 5% are left at the wave behavior. But when you look at the wave result, okay, these are completely incompatible with the firm one. So because we've seen a visibility of 41%, and so attesting the validity of quantum mechanical description of photons and then light in general. Okay, so how to implement this idea once the feasibility has been proved? Of course, you have to go through the key rate, so sizing the telescope, the length of the link, the duration of the passage, and you can see when you can or you cannot actually obtain a key rate. You see the growing distances between satellite and ground. You have a key rate that is generally going down and has some knees with the different wavelengths and different, of course, two choices in the telescope sizes. Okay. Another important point is the your capacity to discriminate the qubits from the noise, so the temporal resolution at the single photon level. And the best result so far is about a quarter of a nanosecond that we obtained in an experiment over 7,000 kilometers 22 years ago, essentially. And then, of course, you need a very good and low noise qubit generators. On this, we introduced a couple of years ago a scheme that is using self-compensating encoder for the three-state, a very compact issue. We call it Cognac, that was successfully used in a demonstration in fibre with quite low QBER. And this idea was further expanded into a system that was world record low in terms of QBER, and at the same time enjoy a stable polarization output, which is crucial if you have to send the qubits down to space from a satellite. Okay, this is called the IPONIAC. Okay, and with this idea, essentially, we have proved that a complete system, okay, to demonstrate the whole business with very low QBER, and we've done a demonstration on deployed fiber in Padova between the Rectorate and the Department of Mathematics, in which we have Alice and Bob done using our patented technology that essentially shared the classical communication on a fiber, an deployed fiber, and that was used to authenticate a rector document. Of course, it's very important, the authentication in this case. We also realized quantum secure video conferences between the director of mathematics and the rector himself, and also we were able to encrypt the utmost security, the one-time pad, some documents. Okay, so if you want to hear more about this demonstration, you're welcome to the talk of Marco Vesani on Friday morning. Okay, and this technology is indeed very ready to be used for application, and on this also we started a spin-off company to technology transfer towards application that are actually looking for the quantum security in the case of ground and also free space and space applications. Okay. Of course, another issue is about night and day use. Okay, night can be quite short for satellites, especially if they are high, and so the issue was to aim at the daylight free space QKD way. Of course, if you know that the spectrum at 1550 is about 1/3 in terms of intensity than at 850, well, you may think of moving the wavelength towards the infrared, and indeed by say having the support of Italian Space Agency and teaming up for the integrated photonics with Sant'Anna CNIT in Pisa, we actually devised and realized a demonstrator using essentially these ideas and having a daylight, also broad daylight with the sun hitting the telescope, a free space link enjoying a very low Q-bar and a significant rate throughout the day. Of course, for this you power up with a very fast and secure random number generator, and we also enjoy having one that was developed, invented, and patented in the lab that also have a world record high speed. Okay, then you have essentially for deployment in urban for practical use, the need of demonstrated this type of detection on ground from satellite on existing building with not so large telescope like the one in Matera. Okay, so 1.5 meter. Of course, a superb telescope, but it's very costly, very also bulky. Okay, so we installed a 400 millimeter class telescope on the roof of our department, and this is on the way for a number of say tests and say checking for quantum receiving. About the future, well, we are proud to be part of this Open QKD project that is the all EU QKD testbed. We have heard of this already previously. That is actually a project that on 3 years demonstrating potential to keep telecommunication, healthcare, electricity supply, and governmental service safe from cyber attack. University of Padua is a sole Italian member, and our duties, our roles are mainly interfacing satellite and terrestrial QKD, and securing space and ground infrastructure, demonstrating the daylight free space link interconnected with fiber link. You can see an image here on say interface between the fiber that comes in yellow here, the telescope there, and testbed replication after that. We have the pleasure also to have the coordinator Anne Subel in the audience today. So the vision is, of course, the one that we described before, that is envisioned by the Commission and by ESA with this SAGA program on the deployment of this. Also, Italy has a project for bringing this idea to space with an orbit demonstration. We can hear about soon. And looking beyond, the global vision is, of course, to be able to share, as Rupert also mentioned, entangled pairs among different locations in the world. And you need altitude for that, okay? But at the end, you may enjoy the most fundamental type of connection and the access to protocols like teleportation between continents. Okay, it is at the moment still a fundamental research. Okay, there's a lot to do to get there. Okay, it's a very ambitious challenge, but also a great opportunity indeed to enjoy this quantum internet, as was depicted in the reference of Stephanie Werner that I mentioned there. So as a conclusion, the feasibility of space QKD has been demonstrated. Novel ideas support compact and efficient payloads. Okay, so going from IUV, the first step, to continental constellation, QKD can be seen as a main satellite goal or even a service from space, as in many other cases of satellite that say help the business and economy at the continental scale. UNIPD is at the frontier of research with the demonstration of technology transfer from labs, so to basic research to spin-off. You will hear soon about that. That is embracing essentially the senior research in our group. Okay, this is just a summary of our path in this space quantum communication starting in 2003 down to the result we have presented recently. In Padua, I would like to mention also that there is a quantum technology research center that embraces different competencies from mathematics to physics to engineering and chemistry. Okay, that I have the pleasure to and the honor also to direct. Okay, we would like to thank our funding agencies, different projects that are aiming to realize this concept into practical application to help the European citizens. And with this, I would like to thank you for your opportunity by showing you on the right part and the bottom part the people that really does the work, and our fantastic team, starting from my colleague Pino Vallone, my new colleague Francesco Vedovato, all the postdocs and the PhD students. Thank you very much for the attention.
Thank you, Paolo, again for a very nice talk and overview of all the activities that you are doing in Padova. It's really nice to see these activities. So let me thank all the speakers of this session. So again, Rupert Ursin, Alan Kurozevich, and Paolo Villoresi. And now I'll conclude this session, and I give the words and the stage to Francesco Cataliotti and Paolo De Natale for the roundtables. Thanks again.
So thank you very much, Davide, and let me also thank all the speakers of both sessions. They have they have done a fantastic job of illustrating the many fascinating aspects and facets of this fantastic initiative. Now we have a roundtable to wrap it up, and where we will also have will be introduced by Paolo De Natale, who is the Italian representative in the Quantum Community Network, and I will leave to him to introduce his sorry, I'm using the Italian word, I suoi ospiti. Okay, so Paolo, you have the...
Good afternoon. Okay, I'm Paolo De Natale from CNR, and we have several important guests at this roundtable this afternoon. We have Pascal Meillot from DG Connect. I can see him.
Yes, hello, Paolo. Hello, can you hear me?
Yes, I can hear you. Okay. I cannot see you, but probably okay. It's the important anyway is to hear you.
Okay.
And, we can hear you well. Okay. And then we have Hannes Hubel from the Austrian Institute of Technology, participating to OpenQKD consortium.
Hello, hi. Paolo, can you hear me?
Yeah, very well.
Perfect.
Good, thanks. Then we have Angelo Bassi from University of Trieste in Italy.
Hi everybody.
Okay, hi. We see you and we hear you. Thanks. And we have Claudia Facchinetti from the Italian Space Agency, RC, also in the panel. So I think we can start in the order. Also, these names are listed to discuss all opportunities related to this very large endeavor that for the first time will be started in Europe, that is EuroQCI, and all related quantum communication opportunities. And so I would like to start from a European point of view with Pascal Meillot from DG Connect. And okay, if you can hear me, you can start presenting also EuroQCI related projects, please.
Yeah, Paolo, thank you. I've seen that in the previous presentations, there were already some explanations about EuroQCI, but just to give some insight about the project itself. It began in 2019 with the signature of different member states, 7 in June, if I'm not wrong, signed a declaration of support for the development of EuroQCI. EuroQCI being a pan-European quantum communication infrastructure, interlinking the different member states on the ground segment, but as you all know, there are some technical limitations on the ground segment, and complemented then by the space segments with a constellation of satellites as we see it. After June 2019, other member states joined this declaration of support, and I'm very happy that now we are 26 member states behind this project. We are still missing Ireland, but we have close. I don't know if there is a sort of background noise when I speak. 26 member states. Ireland is the last one. We are in close contact with them, and we really hope that they will be able to join us very soon for this project. So during 1 year and a half, we worked with the different member states to establish a bit the project, how we see it, how we see the deployment in the groups called Sherpa. Davide and Francesco know that very well because they are the Sherpas for Italy. And now, after 1 year and a half of hard work, we will soon open the calls for the different components of these EuroQCI. So I cannot give a lot of details now because the calls are not public yet, but you can obviously already understand that there will be calls for the national QCI, the development of a national infrastructure in the country itself, and then calls for interlinking these different member states. The space part is more managed by ESA for this project. Here are some elements that I wanted to indicate. Paolo, if there are things I missed or the points you would like me to talk about, of course, don't hesitate to ask.
Let me unmute. Yes, I was muted. So the very general questions can be of interest for the audience. For example, how do you think EuroQCI will improve daily life with this new quantum communication in Europe? Oh. The impact on the society, basically. What's your forecast from the point of view of the Commission?
Mm-hmm. For the daily life, so we have to be clear that at the beginning the QCI will be not for any common end user. It will be for sensitive communications, like, and the first use case decided by the Sherpa are the governmental communication. So in this sense, I wouldn't say that this is a daily user. And also because we have to develop it. It's not completely done in the EU. We have to develop the components for this in the EU. We have external outside EU products, but for security reasons, you understand that we want to develop this QCI with EU products. So at the beginning, it will be for a limited number of users, I would say. But the goal of deploying QCI is not just to have a nice quantum infrastructure in Europe, it's also to attract the business around the quantum technologies. They often say that we don't have customers, we don't have users, so we don't invest so much. So then the EU will put in place the infrastructure with the help of the different member states, and we expect this infrastructure to build and to develop a quantum ecosystem in Europe around that. And in this sense, the daily users then will be impacted, because in terms of job creation, in terms of growth of companies. And when we talk about QCI today, the first service is QKD, so encryption of the communication. Said, I don't believe that QKD will be for any end user, but QCI has a long-term goal of a real quantum internet, and in this, I guess nobody knows exactly how far we will go with a quantum internet, what sort of services we will have. And we can take the example of the computer at the beginning, or the mobile phone at the beginning. It began very rare usage, and now it's everyone has one. Computer is quite common also. So we expect that these quantum technologies, with the different services that the QCI will bring, to come more and more in the daily life of common user, I would say.
Okay, thank you very much. Another question that arises regarding EuroQCI. How is Europe performing as compared to the rest of the world, or the more developed areas of the world? Let's say Far East or US or Canada, in terms of this quantum communication infrastructure.
You have noticed that we are not the only one to think about or do this kind of deployment. China has announced several times that they are building quantum infrastructure with QKD as first service. The US and Canada also have the same ambitions. This is for our international competitors. But in Europe, we also already made different tests. In Italy, you have already an infrastructure from the south to the north. There have been different tests in different countries. In Austria, Germany has the QNet, France is developing their quantum strategy with some quantum communication in it. So I would say that on this level, we are like the others, developing this sort of infrastructure. The difference I would see now is the availability of the technologies. to be deployed. We mustn't hide that when we talk about, and especially for QKD, ready to be deployed boxes, we think about Toshiba, we think about ID Quantic in Switzerland, there is CAT in UK, Chinese, well, nobody knows exactly what they are doing, but I think they are developing their own technologies. So we have all the competencies, all the skills to do the same in Europe. This is nothing to be that can be contested, but we don't have really the commercial product in the EU, and that's the next step that we need to reach. And there will be a call also about that, to have some EU made QKD boxes for the first service of the QCI. So to answer the questions, I would say in terms of knowledge, we are as good as the other, if not better. In terms of market, we are perhaps a bit behind, but we will catch up very soon.
Okay, last question, strictly related to your last sentences. So in terms of verticality of the pipeline for going from components to the market, basically, how is performing Europe? So do you mean we have everything, all the ingredients for building and be self-sufficient in terms of technology, or we still are dependent on other areas of the world from some specific components, and in case which kind of components are the most critical ones that we cannot just produce in Europe?
Yeah, we work with a group of experts. Of course, I am not an expert in quantum technologies like a lot of you are today, but we work with a group of experts to establish a roadmap, to see a bit where we are, what we should develop, etc. So, and the good surprise was that this group of experts established that in Europe, in fact, as you mentioned, components, we have the different components, or we are in the capacity to produce them. We are certainly not in the capacity of producing a lot per week, or we don't have all the production lines to do it. That's something we have to develop, but we have the knowledge and the capacity to do it. So that's why I'm very confident that we will have EU products when the consortium will be established to with different partners to develop these devices, I would say, ready to be deployed devices. I'm quite confident that we have all what we need in the EU to do it. I don't know, it's difficult to say about the future, but perhaps 1.5 years or 2 years.
Okay, thank you very much. So it's very clear. Also, I would say a very interesting and fascinating perspective for this quantum communication infrastructure. Now, I would like to give the floor to Hannes Subel, and probably also discussing the performance of this quantum communication infrastructure. So we are now discussing of the very important opportunity for Europe to build such an infrastructure. But an interesting point that quite naturally arises is what's the performance of such infrastructure as compared also to let's say classical communication, commercial communication available today. So
okay.
I don't know if Hannes Subel, okay.
Yes,
the floor,
Paolo,
please.
I heard your question, and that's of course a very important question, because we're doing this not only because of the science behind it, but because we really want to offer a service to eventually to customers, to the whole society, European people who basically make who realize a benefit out of this QCI infrastructure. And I think we've seen it very nicely in the first talk by Maccarini about the bounds losses. So it's QKD or quantum communication works very differently to classical communication. In classical communication, you basically can have constantly repeater stations, which basically boost your signals, and you basically don't lose your signal strength. So you can go over very, very long distances. This is not the case, of course, with quantum communication, because you encode information on single photons, and those single photons basically get absorbed in the fiber or scatter out of the atmosphere, and you basically decrease your communication rate by going to longer distance. So that's very different to classic communication. And if you look at the current available systems, I think the range is a few hundred kilometers, of course, longer with the satellite, and rates typically in the range between 1,000 bits per second to maybe megabits for very short distances. This is the current level of performance. Of course, this can definitely be boosted by an order of magnitude, maybe even 2 orders of magnitude in the midterm, by either improving the technologies, making more better detectors, basically trying to reduce the losses in the links, maybe also going to completely new protocols like the twin field that we've seen early on. So I think there's definitely a chance to basically go up, but I think we will never reach those really tens of gigabits that's basically possible now with classical communication. But we don't need that either. So I think it's very important what QKD does. It's not encrypting the data. So you basically don't need the full rate of your optical communication to be followed by the QKD system. Because what QKD does, it provides you a key that you use for encryption. So what you do is with the QKD key, you basically feed that key, which is absolutely or information theoretic secure, you feed that into a standard classical encryption algorithm, like for example AES, and then you can basically encrypt with a very relatively short key of, let's say, 256 a bit long, a large amount of data. So for AES, if you look at the NIST standards and NIST recommendations, they say, okay, if you use basically a short 256-bit key, you can encrypt up to 60 gigabyte of data with it. So that means that the key generation rate can be orders of magnitude slower than your optical communication, than your classical traffic rate. So I think this is, not really a bottleneck for QKD, the rate. I think an issue is definitely the distance. I think this is something we have to still address, and it's addressed partly by new protocols, partly by going to satellites and also to trusted repeater schemes. But of course, in a trusted repeater scheme, you always have to make sure that you can actually secure your repeater station, because that's where the key is available again in a classical form. So this has to be addressed. But again, I think crucial point is that you don't have to have very large amount of keys in order to achieve a better security than it's currently, because the key is the main point, because everybody knows that AES cannot be cracked by a quantum computer, or at least I think there's no algorithms around. However, we know that quantum computers can actually break our current public key infrastructure, and that's why we basically need a new infrastructure to produce the keys, not necessarily the encryption. So Paula, did this answer your question?
Okay,
so
I was muted. Okay.
Oh, sorry.
Yes.
So what we wanted to say is we can get very far even with the current system. So even if we don't make technological breakthrough, which will happen, and we've seen really, really good work today by all those different groups, even with the technology now that you can really buy from ID Quantique or Toshiba, we can really make a difference already. We can deploy that, and that's exactly what's planned in the first stage of the EuroQCI.
Okay, many thanks. I have another one / 2 questions. Okay, one is the same question I've put to the previous colleague, Pascal Maillot, on the about a non-European technology for quantum communication. So verticalization of all the pipelines, so substantially going from components to the infrastructure. And the second is the perspective development of single components. For example, what about improvements about sources, really quantum sources, single photon sources, or going beyond the trusted nodes towards quantum repeaters and all the development that can be, let's say, foresee for this kind of technology. What's your view about that?
So roughly, generally speaking, in a QKD system, you basically have the optical part, you basically need electronic parts, you need processing, so computational power, and you need software. And I think in Europe, we definitely have the software part in our hands because we've been working for a long time on it. The pure optical part also, I think most of the time it's still outsourced now to Asia because, I mean, it's just cheaper to get a laser diode there or a piece of optical fiber than in Europe. However, those are, I would call, more or less dumb devices. You know, this you could easily reproduce here, or even if you later on outsource it, I think nobody can really put a trapdoor in there. So you basically still can certify your system and you still have a high level of security, even if not each component, every component is actually produced in the European Union. It gets more tricky then actually if you go into the processing unit, yeah, because in order to basically control your system, read out the data, do some post-processing with it, so you arrive at the final key. I mean, nowadays in many groups it's done on FPGA platforms because, yeah, they're small, fairly cheap, robust, and can be tailor-made to suit your needs. But those mainly come from the US, and basically we already had issues where basically the US basically put some of export ban on it, and then you can have a really wonderful QKD system, all the optics, but you have still no computer to basically control it. And I think that's one point where one has to really look in more detail and see, okay, can we really make sure that maybe we get a producer in or supplier in Europe for those components. But as Pascal said, we had a team of experts which was basically drafting this roadmap, and they basically identified several points or critical components on the system. So I think we still need to basically get some of the manufacturing back into Europe if we really want to be fully self-sustained in producing QKD systems, the current version of QKD systems. Now, if you go then to more advanced systems, like you were saying, single photon sources, entanglement sources, or even then to quantum repeater, I think so. This is much more on a research level still. So I think we will have to wait several years before we really see them coming into the EuroQCI. But that's the roadmap anyway, to basically start the second phase in about 6-7 years time. I think I'm more confident than by then, because there it's really about the know-how, and I think here Europe really paves the way. We're building up a lot of know-how on new protocols, on source developments, and also on quantum repeater work. So I think here I have less worry. Again, some components will probably still produced somewhere else because they're just cheaper there. But I think we have to make sure that we are not relying on a single supplier or maybe on a single country, which can easily say, okay, no, we don't export it. And secondly, I think we have to make sure that those components we outsource from somewhere else cannot pose a potential security loophole in the system. And as long as those two options are fulfilled, I think we can even live with components from outside the EU, which probably will happen even in the long run. I'm not sure if we will get everything back to be manufactured here.
Okay, thank you very much. It's very clear. I don't know if other panelists want to make comments to such questions. Because I think from the other participants, we should look at the chat. let's see if no, I don't see in questions and answers and in chat. Okay, so I would go now to the next one. Thank you very much, Hannes. And okay, we will probably make another round of questions later on. We will see how this roundtable will evolve, because there are many very interesting subjects to discuss. And I would go to Angelo Bassi from University of Trieste. Angelo, are you there?
Hi.
Okay, good. I cannot see you. Let me check.
The video is on. You should see me, I think.
Okay, yes, I can see you now. Okay, very well. Okay, so you are in Italy, but you are also at the border with other countries. So it's interesting also the aspect of interrelation of many different countries that in the future will enjoy these secure communication possibilities. And so how do you see these, considering your position and also the projects that are underway to connect different countries? What's going on in Trieste, and can you explain something about? Thanks.
Yes, Trieste actually is not geographically, not only historically, much closer to Vienna than to Rome, actually. And then if you live here, you can have a feeling that still there is this, I mean, this Austro-Hungarian, I don't know, culture still living basically in the city, although of course we are part of Italy. But that pushes us to look often to the East for various reasons, political reasons, economic reasons, and now also quantum reasons. And there are active players, well, not only in Austria, of course, in Vienna, with not only in Vienna, with Rupert here, many other colleagues, but also in Ljubljana with Rainer Kaltenbeck, in Zagabria with Tiziana Ban. And therefore, because of this, we started some 1 year and a half ago, some discussions about having some common projects between countries. And thanks to CNR, to the group of Ino, to the group of Alessandra Zavata, we started to try to implement the possibility to have some cross-border QKD demonstrations. Some of them were already performed between Austria and the Slovak Republic. I don't know if probably there were others in Europe. And here we are trying to follow a similar path, not only as a demonstration, but possibly as a permanent link. And here it is kind of interesting. I mean, I'm not an experimental physicist, so I take part of this project more as a sort of local coordinator, and so I can see it from a distance and from a bit perhaps from a more strategic and political point of view, not so much from the experimental. And then it's interesting to see the challenges that one has to face, positive challenges, so to say, because one thing is to find an optical fiber within a country, which is relatively easy or not, depends. But then to find a cross-border fiber to be used for a demonstration, this is already something that has to be agreed somehow among the different providers. And then all the things that scale up with that. So, I mean, we have projects for trying to do some joint work, and within also the network capital, which has been sponsored by Vienna and tries to gather all the Middle European capitals. And of course, Trieste is not a capital, but is the largest city in the east, so Trieste is also included as a part, as a local or I mean interregional part of the EuroQCI.
Okay, thanks. So another question that also naturally arises, we have discussed about the hardware and possible perspectives for components, but from your point of view as a theoretician, what are the main challenges of this new endeavor of European scale quantum communication? Also for future developments, so also going beyond the present technology. So from the point of view of a theoretician, what are the main challenges?
Well, I mean, So I would say that the main challenge seen from a theoretician is really to see there would be something amazing if you really can have an extended quantum network which is protected against evil classical environment surrounding it. I think it would be something. I mean, it's, in a way, it's still it's already reality. But still, I mean, if you really have a complicated network, that would be something amazing because we've been used to see quantum mechanics working only in very protected, special situations, which are typically laboratory experiments, and already seen. I don't know, sharing of entangled state by a satellite for thousands of kilometers was already, at least from the theoretical point of view, quite an achievement. If you do the calculations, I have an echo here from someone. And so I would say that that is the most fascinating challenge from a theoretical point of view, to see really a quantum system, a complex quantum system work at the continental level with many nodes and many facilities, and also, I mean, and quantum non-locality with it. If you do entanglement sharing, that's not only a quantum state, but it's a non-local quantum state which is shared and distributed. So that is fascinating. It will come. Sorry.
Okay, and connected also to this first question, the second is, okay, you are, there are many reasons to be fascinated by this new future in terms of communication, but okay, we can also envisage a time in which quantum computers will also populate this quantum ecosystem together with quantum communication. So how do you see this even bigger challenge for communication, connecting quantum computers? And what's in between, in the sense there will be an hybrid situation for quite a long time, for sure, before any further step in a let's say, all quantum system that will be probably later on in the future.
Yes, I mean, my expectation is that if you want to combine also quantum computation with the quantum communication, I think that will be so to say, isolated quantum islands connected classically, if possible. Especially, I mean, quantum computers will be local, and will be connected via cloud, I suppose, in a classical way. I suppose, at least at the first time, will be harder to compute secure information and then to share the secure information one step at a time. And then the connection will come. Now, to which extent, it's really unpredictable. But I don't see. I mean, if there is no fundamental limitation to quantum physics, and I mean, you know that I work on the foundations of quantum mechanics and the possibility that it might break down when the certain level of complexity is reached, but that, I mean, is just a theoretical possibility that is still far away from real experimental verification. So apart from this, I don't see any obstacle to really reaching a full quantum internet. It will be just I mean, I don't want to dismiss, of course, the huge experimental work that needs to be done, but in a nutshell, it's a technological challenge that will be overcome in a way or another. And Europe has all not only Europe, but Europe in particular has all the richness and the variety of research groups and solutions that can allow to arrive to an optimal solution. Actually, I think this is a strong point of Europe. So in a sense, China, or perhaps also US, but in particular China are running faster than us. Well, in quantum computation, also US. Here we have this richness of people and research group that need to be coordinated. You know that also I've been chair of a cost action about quantum technologies for space applications. And from there, I could see that the strength is also a weakness in a sense for Europe. So how to coordinate people towards one common goal. I think that the EuroQCI and all these initiatives are really going in the right direction.
Okay, thank you very much.
Thank you.
So again, are there from the panelists direct questions to Angelo Bassi on the subjects, or also other that you want to try? I don't see any reaction. Let me check also in the chat. Okay. Okay, let me see. Probably there is something.
Paolo, there's one question about AES randomness expansion.
Yes.
At least I see it in mine.
Okay, who wants to answer? Do you see the question?
I see it, yeah. So it says, doesn't AES randomness expansion affect security? I don't know if somebody wants to speak up, otherwise I'll try to answer it. I'm not a classical cryptographer, but from what I know is, yes. So QKD, again, going back to why we need QKD, why we want to have it, it's basically there's a threat level coming from the quantum computer, which can basically exponentially faster solve or crack the public key infrastructure than it's possible with classical computers. Yeah. However, this power of the quantum computer does not affect the security level of AES. So AES is normally will not be subject to breaking by having a quantum computer. You can do maybe a bit faster because you can do a brute search faster on a quantum computer, but that doesn't scale exponentially faster, but to lower power. However, QKD is completely ITS secure, so information theoretically secure, which means that whatever power you give an attacker, he will not be able to break the code. Of course, AES is not information theoretically secure. So if you do basically a combination between QKD and AES, you basically lose a bit of the strength of the QKD key, which is ITS secure. But you basically gain that you can encrypt more information. Now, what you can do is now either you can say, okay, I can live with that because I'm still secure against a quantum computer, or if you really have highly sensitive data, which you want to really say, okay, I want to basically ITS secure that, then you basically have to go back to what Paolo was asking first about the performance, because you can basically combine QKD key generation, ITS secure key generation, with an ITS secure encryption, which is basically the one-time pad. But then you basically need to have your key length exactly the same as your message, as your data that you want to encrypt. Then you're absolutely secure against any possible future attacks as well. But then we are of course coming into a realm where basically that only works currently for small amount of data. So maybe some command control data, which can be absolutely securely encrypted in that way. So yes, AES will slightly lower the performance, but again, QKD and AES is still secure against an attack by a quantum computer.
Okay, thank you very much, Hannes. So I don't see any more questions. If I'm not wrong, from the panelists, no special reaction. Okay, and now we go to the last guest in the roundtable, and now we will move from the ground to the stars, to the space, with Claudia Facchinetti. So there is, I would say, also a little gender imbalance because she's the only lady in the panel, and we hope to give her more time to compensate just for the quantity.
Good morning. Excuse me, but I have not a good network. If it's not a problem for you, I don't use the webcam.
Okay, no problem, no problem.
Could introduce some difficulty in the communication, I think.
Okay, okay. So, okay, to Claudia, I think an interesting question is we discussed it with Angelo cross-border communication, but we can do much more, of course, with the use of space connectivity. And so, Claudia, can you please comment on the perspective of integration ground to space communication networks? What's going on? What also Italian Space Agency is envisaging about these? Please.
There is many interest in the agency in the sector of the quantum communication, and several activity are already in progress in the quantum communication sector in both field, the space and ground. Other activity are planned in the short term, especially for the development of technology in low TRL, but also is planned. There is a plan of activity for the orbit validation of the technology, including a payload for space quantum K distribution for experimentation. Is now under definition. This plan addresses protocol functionality, performance, procedure, security level. The aim is to qualify technology and so on, but also to test the whole quantum K distribution chain, Earth, space, Earth, and also the experiment in all the chain, in the Earth to Earth, using the optic fiber development in the last years, provide us more information to introduce optimization development, and I think to provide real services for the end user of security. I don't know if I answer your questions, but there is many interest in the agency to develop to connect the segment space and the segment ground.
Okay. A related question also for space is how is Europe performing as compared to other areas of the world? I remember, as all of us, of course, remember, the first experiment was the Chinese one with the Austrian colleagues for using space for quantum communication. But now, what's the situation, the European situation, as compared to other areas for space communication specifically?
Well, when you said why the area, what do you intend? What means for you?
No, in the sense, how is Europe performing now, and what's the perspective also for space communications as compared to other developed areas of the world, like Far East, for example, or US, Canada, North America, more generally? So are we competitive? Are we the leader? Do you think we have good cards to play for the future, or what's your feeling?
We are competitive, but we need to continue the investment. Our cards are good. Europe has to stay between bigger players, given also the factor that China and the other countries are investing a lot of money that are bringing forth in scientific and industrial communities. And those efforts are leading to results that could change the future of quantum. Shaping a future is very important, and Europe has to play a leader role in this contest. This is a crucial moment to direct our investment towards quantum technology. The technology can increase at very high rate, and we cannot lose this moment. The European capacities at all levels can guarantee us a strong success in this field.
Okay, so your feeling is positive in this sense. So there is okay.
Yes, because there is a strong attention to what is happening in Europe. In this context, Italy participated with a large subscription on the Force S programs, in particular Saga, with about 30 million euros through ESA program. The cooperation with the European Union and ESA SAG initiative, which include the concept of contributing national mission, but such cooperation called a low sharing of knowledge, a state of art, and can contribute to harmonize the approach for future standard on the technology elements and operations, I think.
Okay, and so related also to this question, do you think also for space that European technology is in a sense self-sufficient, or you are envisaging also strong ties with other parts of the world, like US, for example, for developing specifically space communication technologies?
I think that is needed to invest in the development of technology to low TRL, to start to rest allo stato dell'arte.
Yes, state of the art. Okay, good.
State of the art. And
okay.
But Europe is very advanced in some field of quantum communication.
Okay, good. And also another question that arises in the field is what do you think about the dual use of these technologies? Because EuroQCI, for example, is mostly let's say, civil scientific infrastructure. But of course, space technology also in terms of European Commission is also something with strong ties with defense, for example. So, do you think that the two areas will be both present for the future space communications, or they will be very separated? What do you see from, what's your point of view about that?
But in the field of the security, the dual is necessary. I think that also inevitable. Also, the effort can help to get a better final product and a better goal in a minor time, in a short time. I think that is a good solution.
Okay. Also, on this subject, it would be also interesting if Pascal Maillot is still available in the panel, if you want to comment from the point of view of European Commission.
Sorry, Paolo, you are mentioning now the
dual use technology for in this case for space communication, but this is also a more general question also regarding the ground segment, of course, of secure communication. So what do you think about dual use? Do you think there will be let's say a defense related network well separated from civil applications, or you will see also, at least at the beginning, an intermix in between the two?
Sorry.
Okay.
Please, Claudia,
please.
if you want to complete, yes.
No, for me it's complete, my answer.
Okay.
I think that two area can coexist without problem.
Okay, thanks. Pascal.
For the dual use, well, for the moment, I would say that with the Sherpa, we have not included the military services, I would say. So this is not in the first use cases, but for the future, I don't see why the military also will not come into the market. Now, not the market, but will request the same type of services. Now, having the same infrastructure, mixing the two type of traffics, this will have to be evaluated, as you can obviously guess about security. So I know that the European defense agencies are making some tests with specifically quantum encryption. So there is dual use capacities, I mean, or possibilities. But the QCI itself, as we see it for the moment, is not really open to military department, I would say, for the moment.
Okay, thank you very much. So I think we have just a few minutes. So I'm looking in the chat. I don't see specific questions. So I have time to put another one that is also related to the investment rate that was well explained by Claudia Facchinetti minutes ago. And okay, the question to all panelists, I would say, is the following: do you think? Okay, we have seen in these years the big difference, for example, with respect to US in terms of private versus federal investments in quantum technologies in general, and also, of course, partly for quantum communication. Because of course there are giants in the ICT in US that can invest a huge amount of money for research. Europe, of course, moved mostly at governmental level, investing the European Commission of most of the actions. But now also there is an internal dynamics, no? Because we have seen also the creation, I think in the next few weeks, or probably everything already was signed in terms of quantum industry consortium throughout Europe that was created, and for sure industries will have a role more and more important for the future development of quantum technology. So that's for sure. But so for the next future, so let's say after the end of the present flagship program, that is more or less 7 years since now, do you think the private investment, so from industries, will be really predominant with respect to governmental investments, or what's your feeling? I don't know who from the panel can comment on this point.
I can maybe make a small comment. Hannes.
Yes, please.
So I think, so for the small startups, I think there will be some kind of extra funding probably be available, because I think otherwise it will be very difficult, I think, just by government funding to basically produce a QKD system, because it is expensive, and a lot of design know-how experience has to flow into there to have really a fully working system at a high tier ed level. So I think this is a lot of engineering in addition to basically all the physics and the science has to go in there. And so I think those smaller startups definitely, I think, will need some kind of seed financing from some private investors, and I think a lot of them are looking for that now. Of course, it's not so easy in Europe to basically get this financing, but I think now with this, with quantum being quite accepted and being everybody talks about it, I think that's possible. Now, I think then what we will see probably next is some of the larger telecom operators to basically really start also not investing in building the systems, but I think really taking money to basically buy those systems to secure their own network. So basically, then we are talking about securing of critical infrastructures, and I think this will be a big game changer, because then we are talking probably of a large number of devices being sold, because those companies, of course, have large networks. So I basically see for EuroQCI probably not so important, because EuroQCI, as Pascal said, has the focus, I think, at the beginning at least, of governmental use cases, and this will be probably financed by each member state or the European Union. But I think then the first steps into the private world will probably be those large telecom operators, which basically will buy systems. And then there's the question, okay, who can sell them systems to? And then we hope, of course, that by that time there will be some EU startups which have basically their systems available to being sold to them.
Okay, thank you. There is Angelo probably.
Yes, I can add something.
Angelo, please.
Probably also enlarging the talk to quantum technologies in general, not specifically in quantum communication. I think that actually this is a weak point of Europe. That reminds me some recent articles that I read when comparing countries like UK, US, and Israel and Europe with respect to the vaccination system. So there was this division between pragmatic countries that wanted to reach the goal, and more bureaucratic, let's say, or countries based on rules and regulations like Europe that were more slow in reaching the goal of vaccinating people. Of course, there is a value in rules and regulations, but perhaps a bit more of pragmatism and trying to get to the goal would be useful also in Europe. And I think this is a weak point, not only for, I mean, with respect to the academia, with respect to the investors, with respect to industries. Industries are perhaps, or perhaps in Italy more than in Europe, but I guess it's somehow in Europe more than in the US. Industries are more reluctant to really invest money and take the challenge on board, and are still waiting for public money to arrive first, which is understandable, but they should take the risk. And the same also for all the other actors. I think that as far as I can see, that the European politicians, let's say, are aware of this situation. They're trying to overcome this, but it's partly a cultural problem that will take some time. So hopefully we can win this race. But that's also, I think, this problem adds on top of the many technological and scientific and political and economical challenges.
Yes, just a very quick comment. Some important thinker called Europe a normative power. That is another way to say what you were explaining.
No, there are reasons, and actually there are good reasons for that. The point is that good reasons can also do damages, let's say.
Yeah, of course. Okay, last but not least, I would like to know from Claudia, what do you think about the space segment? Because it's very interesting from the European point of view to see that also reconnecting to what Angelo was saying.
Private investment.
Yes, in US there is an explosion, let's say, of private investment toward the space. And it's incredible for us to see that in place of NASA, there are private companies now flying in between space station and the Earth. And so what do you think in terms of a space segment for the future, private versus governmental investments, please?
But for space, I think that is very difficult. I agree with Anne's Hubble for space is even harder. Governmental investment can push the birth of the market, and private investment will come, especially if there will be a large number of users. SpaceX is leading in the group of the private investment. Constellations are coming, and so I think that we can. It's difficult that European reach the investment of the United States of the China, but I think that we have very potentiality in the development of technology. And think that lower investment, we can reach the same objective.
So you cannot forecast something like a Volkswagen or a Fiat launched to the space like a Tesla. Something similar you don't see, basically. You know that Elon Musk sent a Tesla in orbit, no?
Yes.
Yeah.
So, yeah. It's particular.
Okay. Yes. I think we are quite far away from that. Okay, so I think it's time to stop. So I would invite all the panelists to put a last question, I would say, otherwise we close if there are no more comments from all the other participants. Okay, I don't see any questions. Okay, so I think we can stop. I hope you enjoyed this roundtable, and I want to thank all the participants and all the panelists that spoke in this roundtable. Okay, thank you very much. Bye-bye.
Bye-bye.
Thank you very much.
Thank you.
Thank you very much. Bye-bye.
Thank you. Goodbye.
Bye-bye.
Thank you. Bye-bye.